And I'll also start the recording on the cloud.
Good.
Do we start or we need to wait more minutes?
You can start, I believe.
Okay. Hi, everyone. Good morning, good afternoon. Welcome to the NFIC 2022. So I think that since the COVID-19 pandemic, every month we generate the zettabyte data. And according to the research conducted by Ericsson, the data shows the amount of the data is 20% compound increase on an annual basis. So the key research area for the industry is how we can use those amount of data to improve our daily life and have a more innovation. My name is Gary Ni, and I am the conference chair of the NFIC 2022. The conference is cooperation between the North American Taiwanese Engineering and the Science Association, NATEA, and the IEEE to bring the latest technology and the force of the dream to the community. Our vision is to leverage the new frontier in computing and the communication by being at the forefront of emerging technologies. Today, we have the speakers talk about the AI application in medical domains, machine learning for the misinformation, containment, and YOLO model version 4 used on the object detection and the securing the AI data pipeline. NATEA is a nonprofit organization serving our community more than 30 years. We would like to bring the latest technology to our community and offer a playground to let the younger generation to improve their leadership skills. Thank you for attending this conference, and we hope you enjoy the conference. And I would like to give the handover to Vishnu to give us the introduction of the IEEE.
Yeah, thank you, Gary. Welcome everyone to the 23rd NFIC organized by Silicon Valley chapter of NATEA and IEEE Computer Society. I'm the chair for the IEEE chapter, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE, and the section itself is one of the largest, if not the largest in the world. With over 3,600 subscribers in its mailing list, 1,300 plus paid members, and a strong following of over 12,400 on Twitter alone, the chapter is uniquely positioned by the virtue of its location and available expertise. The chapter operates as part of the global IEEE Computer Society. It's the world's leading organization of computing professionals. IEEE Computer Society was founded in the year 1946 and is the largest of the IEEE's 38 societies. The Computer Society is dedicated to advancing the theory and application of computing and information technology. The Silicon Valley chapter emphasizes all aspects of computing to the local members and welcomes visitors. We organize monthly technical meetings, which give opportunity for professional networking, and where invited speakers from academia and industry share their vision on the computing domain. So with the pandemic, ongoing pandemic, we have switched some of our events to online, like today's event is virtual. It has been a mixed blessing in that we are able to attract participants and registrations from all over the world. Like on the screen, you see the distribution of the location, the cities spread across the world in about 10 or 11 countries across 39 cities from 10 or 11 countries. So that is the distribution of our registrations for today's event. So that is one of the good things that probably happened with this going virtual. This year we started, actually last year itself, the chapter started hosting a Ask Me Anything series featuring world-renowned experts such as Professor Pedro Domingos and Bjorn Schuller. And our next AMA, Ask Me Anything session, will be in October or November. So please watch out for that. The chapter started its quarterly flagship publication, Feed Forward, and an awards program in 2022. So all the slides, in fact, I can probably show our chapter website. So this is our chapter website. All the events are available on the website. And the past events, the slides and the videos from the past events are all also available online. So please take benefit from it. And the recording for this event will also be on our website pretty soon. The chapter is a fully volunteer-driven organization. There are no paid positions. The volunteers benefit by developing their professional network experience and satisfaction, and can also win awards. Like if you see on the screen, our volunteer, Paul Wessling, on the left, is receiving an award for his outstanding service to the chapter. So with that little introduction, a few housekeeping notes before we start. Please remain muted and post any questions on the chat window. If you are on YouTube, please post them on YouTube chat and one of us will relay it to the speaker. And so with that, let's get started with our first talk, which is active learning and explainable AI for medical imaging informatics, infectious disease outbreak. So when we consider artificial intelligence for healthcare, infectious disease outbreak is no exception. We all know that. The talk will begin with machine learning models that help in not only predicting, but also detecting abnormalities due to infectious diseases such as pneumonia, tuberculosis, and COVID-19. Professor K.C. Santosh will open the talk with infectious disease prediction models and unexploited data, where we will learn that predictive analytical tools are close to garbage in, garbage out, at least for COVID-19. That is his claim. Let's hear more about it. He will then also cover multimodal learning and representation based on both shallow learning, which includes handcrafted features, as well as deep learning, which includes generated features, deep features as they are called. So these features typically apply on medical imaging tools. Like in computer vision, Professor Casey, as he is popularly called, will open an obvious question: how big data is big in addition to common techniques? The common techniques like data augmentation and transfer learning. With all these facts, as most of models are limited to education and training, he will end the talk with a statement: machine learning innovation should not be limited to building models. What we need is explainable AI in active learning framework. That's the synopsis for the talk, and the speaker, as I mentioned, is Professor K.C. Santosh. He is the chair of Department of Computer Science at the University of South Dakota. Prior to that, he worked as a research fellow at the US National Library of Medicine, National Institute of Health. He worked as a postdoctoral research scientist at the Loria Research Center, Université de Lorraine, in direct collaboration with industrial partner ITE Soft France. He also served as a research scientist at the INRIA Nancy Grand EST Research Center in France, where he received his Ph.D. in computer science, particularly in artificial intelligence branch of computer science. His research projects, primarily in applied AI, are funded. The value of the funding is more than $2 million by multiple agencies, such as SDCRGP, Department of Education, National Science Foundation, and Asian Office of Aerospace Research and Development. He has demonstrated expertise with 10 books, 220 plus research articles, and 20 plus journal edited issues as of December 2021 in artificial intelligence, machine learning, pattern recognition, computer vision, image processing, and data mining with applications such as medical imaging informatics, document imaging, biometrics, forensics, and speech analysis. He completed leadership and training programs for deans and chairs organized by the Councils of Colleges of Arts and Sciences in 2021, and President's Executive Leadership Institute also in 2021. He is highly motivated and interested in academic leadership. To name a few, Professor Santosh is a proud recipient of the Cutler Award for Teaching and Research Excellence in 2021, the President's Research Excellence Award in 2019, and the Ignite Award from the US Department of Health and Human Services in 2014. So let's hear from Professor Santosh. Over to you, Professor Santosh. Apparently, Professor Santosh has some issues with his throat or health, I believe. So he'll be available for the discussion, but he will be playing a video for us with the content of the lecture. Over to you, Casey.
Thank you. So it was the great introduction. I can tell you that I did that much of work, even I don't know. So you basically reiterate things in a way that I'm a good person. So I really want to talk today in person, but due to my cold cough, a little sickness in my throat, I can't really go for a 1 hour long talk. What I've decided to give you my previous talk, which is very close to what I mean to talk today. So I think this is going to be cool, but I'm going to be here for 1 hour. And for Q&A, this is a 50 minutes talk. I think it's going to be fine, and we'll take Q&A. Thank you very much.
Today, I was invited, and thank you very much for Professor Gudivada. We met back in 2020, sharing the same conference as keynote speakers. I'm fortunate to have you guys here tell my stories about what I've been doing at USD Computer Science. And the talk is AI for medical imaging informatics. And I'm going to focus most of my talks, even though I work on machine learning stuff for healthcare. I'll be focusing on, I'll give you kind of punch at some point. Did you talk about explainability or interpretation kind of stuff? I'll be sharing those things. And
Santosh, can you make your full screen?
Come outside. My name is Casey Santosh from USD. Cool. So everything I'm going to talk is all about me, not about my institutions or agencies I have related with. If you see the left one from your side, that's a beautiful summer campus. And the right one, the winter. We're about to get out from winter, by the way, at USD. That's USD campus. I'm an AI guy, artificial intelligence. So in computing, as a teacher, right, I've been talking about AI all the time. The reason is AI happens everywhere. AI is the future for everybody. There is no program today. There is no project today that can be solved without using any AI guided tools. That's why I said when we talk about research computing back in days, today we want to talk about AI because we want to have fancy name. So healthcare is one of my applications that I've been doing. It's because money is there, right? When there is money, you have motivation. So talking about AI, it hits energy, it hits agriculture, economy, and education. I keep telling people that education is the next decade work. AI for education is a big deal. While talking about document image analysis, you happen to see the picture in here. That was the book based on my PhD thesis way back in 2011. In that book, basically talking about graphics analysis, graphics recognition mostly, and text separation, text recognition. So we will not talk about document image analysis today. We'll be focusing on AI. While talking about AI, the interesting part and that hits everybody is pulmonary abnormalities. If I keep this a little higher, broader, then how am I going to say the same thing is infectious disease, right? Which we call pulmonary abnormalities all around. That can be because of airways, asthma, ear sacs, lung cancer, interstitium, pneumonia, hypertension that hits blood vessels, pleural effusion, so many, and also obesity is another nice, which people don't want to hear. It's just one problem. All these happen to us since the humanity existence. Now COVID-19 is the case that we particularly get hit by since 2020 beginning up 2020. That's a great threat, global threats, and we're still categorized at these COVID-19 in under infectious disease. The question is how dangerous it is, right? What could possibly be our measurement metrics? It's the first thing that we really want to see, how many people die, right? This is kind of self-promotion. I'm going to tell you my story based on my research activities, right? It's not just about textbook. So when I say how dangerous it is, right? How many people die? So when you see classical mathematical modeling, computing mortality and recovery rates, you basically want to refer to WHO, right? How many people die and how many people die after infections. That's basically the mortality rate. What it did not take into account the classical conventional modeling when we compute mortality rate is the average recovery time period. That part was missing in the conventional modeling. What I'm saying is, if you get infected today in the morning, you cannot be taken for computing mortality rate in the denominator part. How many people die, how many infected, that should not be taken from the morning data. Today's morning I'm talking about, because we need to worry about average recovery time period, which is on an average 14 days. Then start looking at mortality and recovery rates for that particular person. It didn't happen in our conventional mathematical modeling. That's why the paper we published way back in 2020, in October, we figured out this, right? When you see classical mortality rate, MR, and progressive mortality rate, PMR, we have not come out basically from COVID-19. It is not the mortality rate. It should be progressive mortality rate, we call PMR. We do science. We basically believe in math, and we take care of average recovery time period. This is how we go. Red curve is our curve. The blue curve is a conventional conventional mathematical modeling computing progressive mortality rate, and the red one is a progressive mortality rate I call PMR. Similarly, when people don't die, we will have to look at the recovery rates, right? It's kind of complementing each other. We didn't say they are wrong. What we say is, in the beginning, when we take all people, infected people in the denominator, computing that MR, mortality rate, it is wrong. We didn't see high number of mortality rate in the beginning, but yes, this should be really high because we shouldn't be taking today's morning infection and number of infections in the denominator, because they don't die. We know that, right? They don't die in 1 hour, 2 hours. So, but in the end, basically, if you consider 200 people in the village, starting from one first person who is just get infected, after 30 days, everybody's infected. So 30 days plus 14 days, 44 days or so, which is in the first image in your image number A, 44 days, you're going to get the whole game from one end to the other end, and you start looking at that's what the mortality rate is. Conventional mathematical modeling and our modeling, they met at the end. It doesn't mean that they're wrong. They never compute wrong, but they did take average time period, recovery time period. That's what the wrong part is about. So at the end, we met each other. That means we're wrong. We're not wrong. So interesting thing is, can we really talk about this is what the mortality rate of COVID-19? The game has not ended yet, right? It's not complete, so we probably not. Is not able to, we probably cannot tell this is what the rate is. It is not like tuberculosis, we really understand the whole game. It is not pneumonia, we really understand the whole game. It is not even established aid for a computing or computational scientist with all possible data and even for mathematicians. So important, the other part is prediction models. I'm talking about what happens next after I see these many data today, right? That's what the prediction is about. And there are, broadly, we have 3 different ways to take a look. Number one, SIR model. Most of the mathematicians, they know SIR model. Agent-based model and curve fitting techniques. All these models never take unprecedented factors into account. For instance, hospital settings for the particular reason, test capacity or rate, daily basis, I'm talking about. Demographics are really important. Population density is important. And vulnerable people, I'm talking about immunocompromised people. Poverty is important. Why? It's because if you don't get money to buy a quality food, your immune system go down day by day, and COVID-19 is not just for 2 days, it's going to go for years. So when we don't take all these unprecedented events, what will happen is we basically scare people. Oh, I predict something, and I had one real nice paper back in 2020, immediately after COVID-19 hits. COVID-19 prediction models and unexploited data. What it does mean is, if we don't take those unprecedented events, like I say, from A to F, they cannot be really parameterized in terms of mathematics, right? No W, no weight, no bias, no nothing. Where am I going to take? How am I going to take no nothing, right? That way, we will get alarming results, and basically we scare people. That happened way back in 2020 in the summer. People never talk about unexploited data, which is the second item here I did just discuss. So important thing for mathematicians is this. How am I going to say this distribution is good? We're always looking at a Gaussian or normal distribution. This is just an example. I'm not saying that this is what you should be looking at. And as an example, we got normal distribution. We have the mu in the middle, which is almost every computer scientist know about that, right? If you have the flat Gaussian distribution and the very tall one, you basically figure out this sparse representation of the data. What we always want is the very, very high, tall Gaussian curve. So most of my data are talking about the same thing. At some point, we did talk about flatten the curve. This is what it is. If you have the curve flattened, all flat curve, basically people will stay away from each other. That means there is no chance that you get infected. In this way, you basically cannot predict without looking at the movement of the people or the crowd of the particular city or region, right? So what does this graph mean is, if you have the tall Gaussian distribution, everybody's talking about the same thing, meaning consistently talking about the same event means good prediction can happen. So COVID-19 prediction model, back in 2021, when I wrote the book about COVID-19 prediction models, we started looking at curve fitting models. Everybody knows linear model, linear regression analysis, and we start looking at increasing the degree of what we call higher order polynomial regression. When I see training data, it's pretty good, but high bias, everybody knows that, everybody's working machine learning models. But again, I fit the data right, don't mean that I predict right, which is basically the last picture in a little bigger than first two, right? So it fits well, that's high bias, but it's going to be real variance. And I can't predict even two days further from the day that I'm looking at, right? So this is basically, this could basically be potentially be the short-term prediction, probably a week, not more than that. So basically build the model that way. But none of the papers or publications that people publish, scientists publish, that they talk about these. And all these papers and everything should be limited to academic education and training, not to look after what the state would like to do after this prediction, because it's going to be missed, right? And everybody knows that all these data visualization happen immediately after we get COVID-19 hits in the beginning of the year 2020. Everybody is going to plot. Social network is full of maze. Everybody's doing this and that, and I ask my students to work on this, just the plot. Give me data. What is the trend? The message is clear here. The message is data visualization is not the prediction. I just plot the data, nothing else. Doesn't mean that I have to go exactly the same way that I used to go, right? If I see this data, then I'm not sure that this is going to go this way, right? It can go other way around. So we clearly made a mess. And I wrote the book and told people that this is data visualization is not prediction. So better we understand the terms and write things in a way that we don't scare people. So most of research scientists, because of the fancy term today, deep learning has been applied at times. That's a horrible story. Think about it. How many data points we have? After 70 days, this is the plot that we've been doing for 98 days or so. First 98 days, 100 days. 100 days data, one data point in one day, right? One data point, one day. How many infected people? 300,000. Second day, 300,000. Let's say 350,000. Fourth day, like this, right? To one data value, one data point per day. If I have 100 days data, we got just 100 data points in there as a feature vector, not more than that, not even a metrics. Deep learning requires a lot of data, which is everybody knows. Because of the fancy term deep learning, people start publishing a lot of papers on the basis of just 100 data points. I'm talking about 100 days and 100 data points. You basically did not predict what happens next. You basically predict the parameters, because deep learning has a lot of parameters to be optimized or tuned. So I said you predict parameters, not the COVID-19 infections in the days to come. It is horrible, right? So too many input. If you have less input, then the size of the parameters, basically predict parameters, not the data. So what it means is, what I'm trying to tell story in here is COVID-19 is data keeps increasing. We really have no data in medical science. Data pour into computing, computational scientist is pretty much hard, and it's not going to happen for some time. So if we have more data, we'll have better results. That we keep saying. But what is important at this point is active learning. Not waiting for data for 2 more years. That by that time people die. So we should be able to have an active learning framework in place. I used to tell the active learning is very important because we need to have machine learns every day by doctors learn from the first day. So we call back in days level few, classify many, right? So just bear with me. I'll come up with medical amazing problems with same active learning framework. So let's talk about images. I gave an idea of prediction. I gave an idea of growth rates because of mortality rate. And I also told you that mortality rate that we keep computing is not right because we didn't take an average recovery time period into account. So think about it, all these abnormalities, and this is basically asthma cases. These are pneumonia cases. This is COVID-19 cases. For computer scientists, I don't see any differences between or among them, among pneumonia, tuberculosis, and COVID-19. For me, it's just a mess, right? So one thing that we should be looking at it, and we know, is the pattern, right? The texture or the shape of the lung. This is what we see because we're computer scientists, right? So we see all these things. It's all about pattern analysis and machine intelligence for a problem. We will understand annotations from doctors, but we don't really need to understand everything end to end. So all these abnormalities come from cavitations, consolidations, this and that. Do I need to know all about it as a computer scientist? I don't care. I don't need to, but if we need to really follow clinical procedures, we basically have to look after this. That's what we call interpretability. And sometimes we call explainability AI, because we want to make sure the doctors are going to be convinced the way that we proposing algorithms for them, so things can be commercialized. If you see abnormalities in first 2 cases and the normal, you happen to see lung shape changes, you happen to see texture changes in the lung region, and so on. All right, they're pretty much easy. So first thing what we're looking at is a lung section. We're talking about pulmonary abnormalities. So basically lung section, lung segmentation is really important. So that's what we do. We did automated, fully automated, and looks like, wow, the shape of the abnormal lungs are kind of, a little skewed. I mean, it's not what we really want, but this is what happens. So figuring out all these things, then when you're back to computer vision problem, it is all about symmetric problem, right? If you see symmetric problem here, let's have 2 lung sections. This is one lung section, the other one here. I'm showing my hands. One is the right lung section, left lung section. If I'm looking at the symmetry between 2 lung sections, you're basically overlapping those things. That's what computer vision symmetricity is about. And we published the paper way back in Transition Medical Imaging in 2018. We're looking at tuberculosis problem. I'm not talking about COVID-19, but I'll reach COVID-19 in a band. So look at this problem here in the first picture. You happen to see the red line passing from one left end to the other end, right? Horizontally. Basically, you need to look after line of symmetry for a scene in computer vision. It's pretty hard because sometimes you need to go a little down and move. It's kind of bumpy, right? So for second image, you just need to have one point and just vectorize it. Third, you just need to worry about the thorax of the beautiful butterfly, and you happen to have this, take a look. Oh yeah, symmetric, nice and easy stuff. In our case, if you look at the problem, it's more easy because you do lung segmentation. They're red in color here, And after that, you just happen to do that like a book, right? 2 pages, go here. Oh yeah, they fit. That means pretty much cool. Symmetry can help us understand if there is a problem. I'm talking about normality in here. So how am I going to do? We try to figure out the clinical procedure in here. The clinical procedure, basically, doctors get the report. I'm talking about chest X-ray, and look at both sides. If it's a problem here, how about the problem on the other side, right? They look both sides this way. That means we should be looking in a way that the doctors will be convinced. So the algorithms basically looking at the low-level shape and size representation of those long sections. All about centroid, bounding box, orientations. Let's talk about, everybody can do it. A little high-level shape representations. Now, most of the computer vision scientists in object or image recognition, they understand this belongs in a shape context invented or discovered by Bellunzi et al. Way back in Palmy paper. I think 2000 or 2001, if I'm not too old, I still remember that. It's talking about the boundary coordinate of the long section, and look at log polar representation from the point where I am, meaning the center. So I keep moving with the same tool around the boundary and looking at this long section with the high level shape representation. This is how it goes. I will have the point, coordinate point, location, and the tangent in every position. So that way I can match. If the matching don't produce any cost, then that's where the matching happens. If we have some cost we need to pay, then that means in this case the shape context cost is $12, which is 0.12745. Probably you've seen there from a distance, right? So here there is no real math. We still get these two things, these two long sections matched with the cost of 12 cents. Similarly, when you take a look, all these ribs, right? We'll have the ACE map representation of the long shape only inside the long section, and look at whether ribs can be visible. If we have a texture change because of abnormalities, the ribs you cannot even count, right? It's a high-level representation. We call ACE map representation of the long section, and try to look at the orientation of the ribs. I'm talking about the orientation, meaning if the rib I can see, the orientation is always like that, right? Because of the texture change, textures, and I would say this, ACE map is the derivative of the textures you have in the image. If the textures change, ACE map gonna change, right? Gonna be changed. So that way, if you see, just follow red and blue histogram, because we're doing here orientation of gradient. In terms of histogram, the blue histogram is coming from blue long section, which is the left one, and the right one is, and then the red, which is going to be there. Basically, when we do symmetricity, you don't really get high-level symmetric value in here. There's something wrong. Same for radon transform. Everybody knows radon transform, and this is the beautiful part of the radon feature, where the radon transform was developed way back in 60s, I believe 50s or 60s, for medical image processing. So why not we take this advantage of the radon features, looking at the core, I mean the feature vector from red and blue from blue long section, right? And see the down one, the bottom one, you happen to see there is a symmetry, a high level symmetry, but the upper one you don't have, right? We talked about symmetry in here. What is missing at this point, like a doctor's doing, is a Garo filter. I'm talking about texture changes. Did I say texture? Yes. And texture change in chest X-rays. Remember, I just use Garo filter and just make them partisan. And then I'm trying to help understand if I make them partisan, do they go and fit? I don't know, maybe not, right? So if they don't match based on their partisans, a corresponding partisan, then it's not going to be good match. Like I said, I'm trying to help you understand by taking a clinical notes, the clinical procedure, like doctors looking at everything, shape of the lung, so texture changes, everything, right? I do exact same thing like doctors do. This is, we follow clinical procedure. So we see interpretation in here, interpretability of the model is here because we exactly follow clinical procedure. So then we start having a feature, we have machine learning models, and we apply all this possibility and try to compare, because there are some people way back in 2017-16, people start looking at deep learning or deep convolutional neural network. Before that, nobody has tried deep learning for medical imaging. Reason, explainability, right? So we tried all these things. We probably got good results. We're not talking about it because numbers are there, paper published. We beat, they got beaten. We don't want to talk about. We just want to talk about, did we really follow clinical procedure and things are convinced for people to get him? That's what we want to talk about. Results are good. Our area under the curve, ROC curve is really better, which is what we call based on the random forest MLP Bayesian network. Like I said, we're not here to talk about why not use other machine learning models. And my response to most of them is machine learning innovations should not be limited to building models. We're talking about concept. We're talking about interpretability. We're talking about explainability and so on. We're not talking about just building models. I beat you, you beat me, who cares, right? Then things not going to be commercialized. Other important stuff that we would like to see in medical imaging is cross-population train and test model. Right, starting in Wuhan, China. I don't know, I can tell the name here or not, but not without politicizing things. That's what WHO said. How about we have the model ready in China the day we get enough data and apply that in Italy? Can we do this cross-population trend test model? In healthcare, medical imaging, in medical imaging problem, it is pretty much sensitive, because of demographic changes, different people, different size, and also different machines, right? Change in intensity values and so on. Do we have such models? Never. So in my lab, we basically want to try and see, did we really, want to get that kind of stuff, right? Do we really want that? And we say, okay, let's start with tuberculosis. This is the tuberculosis data. We didn't have COVID-19 data back in days, and we'll start with the Montgomery County, USA, and test in Chinese data, and vice versa. We feel like a silver lining, or encouraging results. Oh yeah, it's possible. Like machine learning could work, and we'll come up with an idea of this. What we've been doing and doing until this time is, we try to really follow clinical procedure like doctors do. They read the chest X-rays exactly the way we develop algorithms, right? Now, if we want to try two different data sets coming from two different regions, two different populations, because of machine change, demographic change, and everything, man, the handcrafted features is not going to work. Feature engineering is just done, because you do feature engineering only after you see from your eyes, right? P-Hug is good, GIST is good, Gerber filter is going to work. Now, how am I going to know all these things? Because I see data. But I can't, I will not be able to see all kind of data from here, living in the States, and from India, or from Malaysia, or from Europe or Africa, right? We can't do all these things. So what I say is no to feature engineering. Now it's a time for us to move a little down to deep neural network, so machines can figure out distinguished or distinct features for us to go for the right classification. Back in 2020, we start this, we publish the paper, and the paper says pretty good deal, because we come up with the an average results of 95% area under the curve, which is, again, I said, silver lining. What is missing in the game is foreign objects. Biomedical and non-biomedical foreign objects happen in chest X-ray all the time. But when I say biomedical, what are they? Maybe pacemaker, because you need to have those pacemaker stuff, because you really need to have, because you're in an emergency situation. The pacemaker needs to have to make you alive. All these wires kind of cables happen because we're in certain conditions, right? Similar nipples and so on, coins, jewelries, all these things should be extracted, detected, and localized. So we understand these are not abnormalities, right? These things to be done. So we did that kind of stuff in my lab, and pretty much cool. And we published the paper way back. Academia is all about publication. We don't make money, right? So back in 2020, we start looking at, okay, how many people can really talk about COVID-19 or using AI or data science tools? And then we come up with these two books from different experts, and we reviewed and we edited the book coming up. Like I said, at that time, I was looking at a lightweight deep neural network. Anybody can implement, but can we look at the lightweight, the really light possible weight, right? For this one, we come up with inception-mate, and we make it truncation inception-mate. That's what lightweight is about. This is what we do, and we published the paper back in 20. And these are the data sets. We start looking at COVID-19, pneumonia, tuberculosis, and healthy. Why do I have so many multiple, right? If we say COVID, non-COVID would count on pneumonia, all kind of cases, because our intention is, our primary objective is to detect COVID-19. How about just COVID-19 healthy cases? That would be a nice idea, right? COVID-19 versus healthy is going to be a really straightforward problem. Anybody can get 100% accuracy, right? But we would like to have COVID, non-COVID. Non-COVID can contain any type of abnormality in the game. So we come up with this one. Data is purely small, which is 162, not too much, because that time, way back in 2020 in summer, we didn't have that much data. We come up with this we don't want to talk about. And we got area under curve 99. I'm not really proud of saying all these things, but I'll tell you, the results are encouraging. So then we were looking at starting from 25 image data in here, and we'll move up to 162. That time we are we got the experiments on large data set, which is 162 at that time. We're talking about literature, right? So I was looking at myself, my students, come on, how big data is big then? Where are we going to start? Nobody say that it's a big data issue. Everyone knows that. And I come up with a paper, COVID-19 imaging tools, and I was telling people how big data is big. Where are we going to start? Sometimes big data is a buzzword, everybody knows that. And I came up with this one, and this is like a nice literature review. That many papers published, and if you see from 71 images all the way up to 18,524 images, do you see big data? You need big data to improve the performance. That don't make sense because more complication happens. And people say, oh yeah, when you don't have big data, you say, I need big data. When you have big data, you say, I put more complications in here. So interestingly, we start looking at both X-rays and CT scans. Everybody says the same thing. Oh yeah, we have data, which are complications. So what do you really want, right? In medical imaging tools, data sets important whenever we deal with machine learning models. Nobody in all these papers I'm talking about, nobody was talking about model fitting issues. Everybody was talking or aiming at publishing papers because I beat you. You didn't beat me, right? That's what the problem is. And everybody's looking at data augmentations because we don't have enough data. Let's augment the data then. And what is data augmentation for computer scientists, computer vision scientists? It's about just changing pixels from here to here, rearranging all possible in all possible ways. Did I say right? Yes. So rearranging pixels in all possible ways from the cyst X-ray. I'm talking about just cyst X-ray. CT scan is also there, right? If you rearrange those pixel intensity values in all possible ways and make the data set big, does it really mean that it is a COVID-19 clinical manifestation? What is the clinical significance? No way. Who's going to annotate those? Did you say that this is also a possibility of one type of clinical manifestation of COVID-19? No way. Data augmentation can improve the results, but it is not explainable. Nobody's annotated those data after augmentation. No way we can do it. Then how about transfer learning? Transfer learning is very important in computer vision. That's what the game change happened way back in 2015, 16, and all the way up today, right? But how about transfer learning COVID-19? I don't think it's going to work. The reason is transfer learning is going to work. It's basically, I said, GIGO, garbage in, garbage out. It's about beating you, beating me, beating everybody else. So we'll talk about this one. Did I say cross-population tools are in place? No. Did I say active learning? We'll be talking about multimodal and multi-channel data. The first time after COVID-19 hits, in March 2018, I published this paper, and this is all about what we need for us today in this time means March 2020, is we need AI-driven tools, and the driven tools require active learning and cross-population trained test models on multitudinal and multimodal data. What do I mean is, this is the paper I cited, and so on top of 1% academic field of clinical medicine, based on this, this is coming from Web of Science. This is the framework. I said active learning is required. Let's be honest in here. In 2020, beginning of 2020, after COVID-19 started kicking our ass, think, do we have COVID-19 experts in the medical field? Probably not, but we do have infectious disease experts. When they see COVID-19 problem, the first time, they wait for a couple of days. It's weird, unusual, never seen before. That's what doctors say. I didn't really mean that they don't know. Okay, don't take me wrong. Where I said, wow, unusual, never seen such kind of pneumonia cases, because COVID-19 will bring pneumonia too, right? A little different, unusual. From that day, medical doctors started to know, by collaborating with other medical doctors across the globe, this is weird, a little unusual than we used to learn, right? Then they started learning. If we allow machines to do the same thing with the help of medical experts, today, our machine is ready and becoming an expert like medical doctors we have today, right? What I'm saying is, if you see a nice clock in there, over time you get data. Data type 1 could be medical image data, which is chest X-ray, CT scan, RT-PCR, these all possible data types for COVID-19. Doctors were not ready in the beginning, and they start learning everything from first day till today, and they're experts. If we allow our machines working together in parallel or together with the doctors, in the active learning framework, having a feedback mechanism from doctors, if I make mistake, I mean machine. Our machines are today ready for the world, for any infectious disease outbreaks. That's what I'm talking about in active learning. Our machine and we should not wait 3 years or 4 years for enough data and build the model and make it happen. By that time, people die. There is no point. That's what the paper about in March 18, 2020. And I was talking about multimodal data. Reason is, if you have one data type that is chest X-ray, you always have great results. I didn't say that we need to have more data, but I did say having multimodal data, different modalities, will talk about exact same event. That way we can aggregate or integrate different decision-making from different data types and have higher confidence. So we will never miss the thing that we will be looking at. That's why I'm talking about this chest X-ray and CT scan. One example. An example is this beautiful example. If we have a clinical manifestations from both type of modalities, how about I integrate both clinical manifestations in my model? That's going to be beautiful, right? Because they talk about the same event. Event E is COVID-19 here. So we're looking at it, CT scan, chest X-ray here, right? So we have not enough data, because in academia it's beautiful that we can start from any data we have. And I say this is just for training. I'm not saying that this is going to be commercialized, this and that, because we're looking at silver lining possibility, right? So we come up with this one, we publish the paper. The idea is to have just one architecture for both CT scan, for both modalities, CT scan and chest X-rays, right? It's beautiful. What is missing all time here, I did say I follow clinical procedure, I try follow, but I didn't say that where the disease and pathologists lie, right? I didn't say that. So when you see explainability explainable AI, people love this image at the end. And we start looking at this. And okay, fine, let's localize. We used to say, we were trying to be honest way back. We said, yeah, let's figure out what the pathologies are. And here is the heat map, and the heat map's basically giving us an idea. These are the location where the clinical manifestations of pathologies are. And people say, this is explainability. I have to tell people that, and I always want to tell people that explainability should not lie in the eyes. All these mathematical models, we do in neural network, and this and that, equations don't lie. It does mean that they are not interpretable. So we believe in eyes again. When we believe in eyes, what will happen at the end is we should forget deep learning as well. Notification engineering is not going to work. That's why we are running in the wrong directions, telling people that all these models are black box. No, we do white boxing. We'll talk about this one. So first thing, machine learning innovation, right? So we have data, we build the model, we have all the data, we publish. Pretty good. That's what Academy is about. Then what about interpretability, which is good. We also talk about it because, like you say, are we really doing black boxing here? No, black boxing is not there because we believe in math, and everything inside neural network lies in math too. We make exact same mistakes over and over, right? We're consistent making mistakes. That's basically, it's not black boxing. But how about white boxing then? Is it the white boxing? Because you see those things? Then if you see those things, why not we talk about handcrafted futures? Go future engineering, beautiful life. But we didn't believe that too, because we worry about deep learning. We worry about missing information. And if we are coming from physics background, in physics we say light strikes the object, and we see objects because it's going to hit our retina. If we believe in eyes, then it's fine, right? But some of the pixels that we don't see, they're going to be extracted because we throw deep learning model really highly deep learning models into place. So what I'm saying is, machine learning innovations should not be limited to building models, not because these. So we've got more works, and we'll try to see if I can make more explainable, which is published in a student conference, which is, I forget the name of the conference in here, IEEE-SMC. And the other paper that we're looking at, because in South Dakota, we have more lung cancer patients in here. So it is better we prioritize them. The idea is the long-term goal is to prioritize high-risk patients from future infectious outbreak, disease outbreak. COVID-19 is just an example. If we happen to have other type of COVID-19 infectious disease outbreak in the future, lung cancer or other immunocompromised people should be prioritized, and we should have a different hospital settings for those people, right? So that's why I said, what is the difference between lung cancer and COVID-19? How can we prioritize if we are going to face a future possible infectious disease outbreak? And the paper is basically in price. It's going to be published. It's taking a lot of time, but I'll accept it. Other thing is, like you say, detecting abnormalities is important, and classifying them, not just healthy, non-healthy, classifying them either it's COVID-19 or pneumonia and tuberculosis. Why do I say that? Is pneumonia, all pneumonia types are not COVID-19, right? COVID-19 brings pneumonia. So can I make a classification? It's important. And same thing for tuberculosis. Tuberculosis will bring pneumonia, but my kind of pneumonia could not potentially be tuberculosis. So important thing is this: we did talk about multimodal learning representation. While talking about multimodal learning representation, this is the token message for people. Here is, if we really want to talk about smart healthcare, we should not just limit ourselves on one data type, because there is no point that we'll be having a confidence in terms of decision making. So what I'm saying is the following. Let's say I have an event E, meaning disease type G, let's say, right? I start looking at my appointment with the doctor, starting from the picture on the top. I'm talking to my doctor, I call, I'm talking to my wife, For my kids, I'm going to go meet doctor. All these speech data should be recorded because the way I'm talking depends on what I have in my body and my neurons, right? The speech data today are not recorded because the doctors don't need that. Doctors just need those sensor-based data and then prescriptions what they prescribed. And all these are maybe imaging data and so on. But how about this data? This data can tell us a lot about the event happening in your body, right? The way you talk to your neighbor, the way you talk to your spouse, if you have HIV positive, just an example, is different, right? So space data, you're talking to people, having all types of sensors, data and everything, all these tools available, have the deep AI model or deep learning model placed in between, and look at whether these all modalities of different types of data can tell you consistently about the same event. Yes, it's going to tell. That's why the consistency checking is very important for grant writing. It is a part of grant writing. Basically, well, I really want to have this smart healthcare happen by 2030. For any disease type E, all these data types are important because I'm saying we need to look after the consistency checking for every data type, every possible data type. I'm talking about modality and the visualized data visualization. If my speech data and the way the people, the doctors taking my data from sensor-based instrument, I'm talking about equipment, are they talking about the same thing? Yes, of course, because it's very important. And our decision making should have no bias. If you have HIV positive, I don't want my doctors just come and pat on me in case you don't worry, you'll be fine. No, I'm not fine, man. You just tell me what it is. So because we need to look after the population screen. Talking about big data, when I spent 2 or 3 minutes, not more than that here, a big data happens because of population, okay? And big data happens in healthcare. The day you born, you have to get registered for anything, starting from head circumference, waist, length, size, everything. Then when you see all different data types, numeric data, text data, image data, all possible data types in there, and in numeric data, it is important for us to understand the sentiments by seeing the numbers, also from blood pressure, numbers also from weight and waist, height, BMI, all these numbers, but they are different units, right? Metrics measurements are different. So we can't just put them in a data analytical tool and play and have fun. That is basically GIGO, garbage in, garbage out. That's what the computer scientists is saying. Image data, too many different types of the data. Text data, really important because that's where the PubMed Center repository at National Library of Medicine exists today. So I used to say that we understand data types, we understand numeric data, text data, image data, and everything. And then, by the way, everybody knows in 2005, and before that, we love to say we are database engineers. Now, all of a sudden, overnight, they become data scientists, doing nothing. We're happy with the sexy term. We need to worry about all these things, and we academicians should be able to make them understand, my friend, database engineer is not data scientist. Right? Take a message. Active learning is the must for today. Healthcare, that's what it should be. We should be able to make people convinced and make things commercialized. Like doctors started to know COVID-19 after a couple of months because we were in trouble. What is this, right? Like doctors, and they become experts over time. Our machines can do. So active learning is very, very important. We want medical experts work with active learning framework, make them happy both side by side with the feedback mechanism we call closed loop control system for undergrad, right? So predictions. We don't really want to do GIGO and scare people. And think about it, like I say, if it's a simple problem, you don't want to take your deep learning sort out. Here are 2 problems in here. Machine learning, too small, we say low-level machine learning is going to be okay when the problem is not complicated. We don't want to use deep learning models for prediction because we don't have that many data points in there. Number 1, if you have a coffee, you don't want to take shovel out to have the coffee or sugar in your coffee mug. While if you have to clean the driveway, you don't want to take a spoon. You need to shovel. Shovel is deep learning models, I'm saying. So everything that I'm talking about is all about these books. These books are real cool books that I have been spending quite a good amount of time understanding data and writing all these things, mostly for COVID-19 medical medicine. And more self-promotion, I just don't want to say that this happened because the university would like to have me promoted, so they collect all this data from me for the how to say, advertisement. So we got more enrollments coming out. Other than science, I run 5, 6, 7 miles a day. This is me, and I want my son to do the same thing. That's what the life is about. And I do run some typical and good conferences. We're going to have one conference in Texas, a recent trends in MS process pattern recognition, which is in November. Please do come. And we're going to have this IEEE 35th International Symposium, computer-based medical system CBMS in China this year. I did that one. I organized that one in 2020 in my clinic, Rochester, Minnesota. Thank you very much. And I think we have some time for Q&A.
Okay, yeah, sounds good. Is anyone have any question? I didn't see any question on the chat window.
Yeah, there's no question on the chat window, but Casey, I was just curious, how do you manage the legal requirements surrounding the privacy of medical information and all that with the data sets?
So thank you, Vishnu. You're talking about medical image data site. Are you talking about that?
Yeah, and then the cross-country things and the legal framework surrounding that.
Correct. So most of the data sites we used, they come from NIH and they're public, meaning they've been gone through IRB control and everything, so they're publicly available.
Oh, okay.
The sensitive part in healthcare is, or the expensive part in healthcare is the data all the time.
Yes.
Right? If the data is not there, there's nothing to do. If you have, like I said, if you have small data, you say I need big data. When you have big data, you say too much complications. No, we need to think about something. So we always try to blame things here and there. But our data sites, just to run the system or the research work in lab, basically limited to education training coming from public data site.
Okay, thank you. I have more questions, but I guess we are over time. So
sorry about that, because I can't really manage things. Sorry, thank you.
No worries, thanks. Thanks for the insightful talk.
Good.
Okay. Yeah, we have the recognition. Thanks for the Casey Santosh, Professor Casey Santosh. We have the recognition. Or would like to present to the Casey Santosh. Vishnu, are you able to present? I found I'm not able to share my screen, but if you have time, you can present our recognition. Yeah, thanks, Casey Santosh. Yeah, I think that it's very useful, and I believe I heard a lot of doctors told me they spend a lot of time to read the image from X-ray or from the CT, but your research definitely will help the doctor reduce their workload, and they can focus on the patient. Thanks for your talk.
Yeah, actually, there is a question on YouTube as well. While I shared my screen, maybe I can quickly relay the question on the YouTube. So it says, we are PRR, PMR for other ailments like asthma, match. COVID-19 and all that. So does that make any sense, Casey? Or
correct. So if I understand the questions correct, then I can tell you something. Let me rephrase, or let me tell you things so the questioner can understand a little from my side. If the game is not complete, there is no point to say is the mortality rate. It should be progressive because it can go down all of a sudden because we didn't see this is what it is. How do we say the light rate, right? We say the rate of whatever, because we make the game end from starting point to the end point. The game has not been ended yet. Sometimes going up, sometimes going down. That does not let us do, this is the mortality rate. We should be saying progressive. I'm talking just scientifically, but we can still use mortality rate. Don't make any sense to us, but that's okay. Scientifically, it should not be definite mortality rate. It is a progressive mortality rate. That's why we provided synthetic data of 200 people in one village. Starting from first day, one guy is infected. In 30 days, we believe, we assume that everybody's getting infected, right? And adding 14 days, meaning everybody's getting infected, we will know 44, 45 days how many people die and how many people recover. So we should do both things at the same time. That way, we can say for the village, if that is the world, that's the mortality and recovery rate, but not real mortality. It's a progressive one. Thank you.
Yeah, thanks. So hopefully, Gary, are you able to see the certificate on the?
Yeah. Yes. Yeah. Thanks for the Professor Casey Santosh. Yeah, would like to present our certification, this recognition to you. Yeah, we will send you this file after the event. Yeah, thanks for your time. Thanks for you coming with us today.
Thank you very much. Beautiful certificate, Vishnu and Gary.
Yeah. Yeah.
Cool. All right. Thank you very much.
Yeah. Thank you. So we have the next speaker. We tell us about. We give us a talk about misinformation containment. So this misinformation containment was already proven to the NP hard problem more than a decade ago, and the Dr. Vishnu S. Pendyala we present some future direction of we presented some future direction and explain why this why loss is hoped for us today. Yeah. So let me introduce the Dr. Vishnu Pendyala. He is the facility manager of the Department of the Applied Data Science of San Jose State University and the chair of the IEEE Computer Society Silicon Valley Charter. He has over 2 decades of experience with the software industry as a leader, like the Cisco and the Synopsys in Silicon Valley. Dr. Pendyala also serving on the board of the director Silicon Valley Engineering Council during the 2018 to the 2019. During his recent 3 years term as ASEAN Disputed Speakers and as the research and the industry expert, he already given more than 50 talks. Yeah, he hosts the MBA in finance and the Ph.D., MS, and the BE degrees in computer engineering from the US and the India universities. Yeah, let's welcome the Vinish and Vinish S. Pendyala. Yeah.
Thank you, Gary. Thanks for the introduction. Hello, everyone. So today's topic is a really hard topic for many. Like Gary mentioned, misinformation containment has been proven to be NP hard more than a decade ago. So it's a complex problem. And we know that machine learning converts an intractable problem into a tractable one, right? That's the power of machine learning. There are many such successes using machine learning for intractable problems, right? But did it succeed with this particular problem of misinformation containment? It is anybody's guess, right? Even the layman can see that the problem is far, far from being resolved, right? And misinformation containment is undoubtedly a complex problem to solve. And appropriately, it has attracted plenty of attention from the research community. So just to impress you about the problem, this screenshot was taken on July 23rd of this year, 2 months after a video was posted on YouTube. So what we see here is the metadata of a fraudulent upload on YouTube, faking as a popular Indian movie, Kashmir Files. As you can see, it has attracted several millions of, how many is it? 18 million, almost 19 million views in the 2 months. And 289,000 likes. So this is the movie, actually. So this is still there, surprisingly. You can see the movie there. But my point was that even a fake movie like this is able to attract lot of interest. See, this particular user has 123,000 subscribers, and in 2 months it has attracted 15,250 genuine comments. So comments which indicate that they believe that this is indeed true movie. And you can see that the comments also received several likes and then several replies and so on and so forth. This is a Google search for the phrase fake news. It was done on the 23rd of July. And it resulted in 81.5 million results. And Seattle Times has the week in fake news section. So it is that big a problem. Fake news is hardly resolved. It's a serious problem. So I'm a great fan of quotations, and this quotation is from an infamous person called Andre Sepulveda. So this person rigged the elections throughout Latin American countries for almost a decade by posting misleading information on Twitter and other microblogs sites or social media. So the quotation goes like this: when I realized that people believe what the internet says more than reality, I discovered that I had the power to make people believe almost anything. So that is the extent of gullibility of the people and the power of the social media and internet. And this quotation is not new. It is at least 5 or 6 years old, or maybe more. So that is the problem we are seeing today. Even the presidential elections, it has been proven that this person actually manipulated the presidential elections, influenced the presidential elections. So he was actually put in jail. I think right now he is in jail. But the fact is that his work actually changed the outcomes of the elections. So it is that bad. So how do you solve this problem? So a quick insight for the non-initiated or uninitiated. How do we know what's true on Twitter? So how do we classify tweets as true or false? Twitter is an important candidate for enforcing veracity. We all agree with that. So we will use Twitter to briefly see how machine learning can be used to detect whether a tweet is true. A very quick overview of machine learning. So the first step is to collect ground truth or the training data set. So that is the toughest challenge because you need labels for the data you collect. We are going to talk in a little more detail what it means, but ground truth is like the frame of reference, right? Like the model apartment that the apartment management shows to help us learn about the remaining apartments, right? When we go to buy or rent an apartment or buy a condo, there's a frame of reference, model apartment. So ground truth is like that. And from that data set, we build a model. Of course, before collecting the data, we need to know what to collect from the data, right? So we extract features. So we need to do some feature engineering, extract features, and then get the values for these features in our ground truth. The next step is to learn a model using one of the algorithms. So model is like a machine learning model, right? It's typically it's a bunch of numbers called parameters, and you plug in those parameters into some math, you automatically get the classification. So that is the idea behind a model. And once we have the model, we do validation. So model validation is a process of evaluating a trained model on data that the model hasn't been trained on. So there is a section of data on which the model is trained on, based on which the weights are extracted or derived. And there is another part of the data based on which the model is validated. So it's like two kinds of exams for students, right? So there's a sample test and there's a real test. So answers are provided for the sample test, but they are not provided for the real test. So this happens in certification exams, competitive exams like GRE, SAT, and so on and so forth. So the real answers are never known for the real exam, right? But you learn based on a sample test. So the sample test is like the training data set here. So we fine-tune the models. The way we fine-tune is by doing multiple things, like changing what are known as hyperparameters or changing the algorithm itself and so on. Mostly it is fine-tuning the hyperparameters. Every model has some parameters which are beyond the normal parameters. That's why they are called hyperparameters. So these hyperparameters are typically manually determined through the process of validation. So that is what is validation. Then we evaluate the model and then fine tune. So that's what goes on. So the whole idea of learning is continuous improvement and refinement. So we keep fine tuning. That's why there's a loop. There's an arrow tracing back. So it's actually a loop going on there. So the first step is to do some feature engineering. That is, determine what features will help us achieve our goal, right? Machine learning algorithms depend on features extracted from the real world to classify the data. So these features are indicative of the class to which the data belongs. So just like the lie detector, right? In real world, how do you determine lies, whether a person is telling a lie? You use a lie detector sometimes, right? So this lie detector works on the features. So the features of the person, like his heart rate, pulse rate, perspiration rate, things like that are measured. And based on those features, it is determined whether the person is telling a lie or is telling a truth. He or she is telling the truth. So these are some of the features that indicate the veracity of the tweets. These are quite intuitive, right? For instance, a Twitter user who is reputed as measured by the features listed in the in some of these boxes is more likely to tweet true, verified statements, right? So quotation marks and using images and numbers for that matter. I mean, numbers sometimes lie. There's a famous saying about it, but we can presume that numbers typically don't lie. So presence of numbers, quotation marks, whether the tweet is pinned, all these are features which can help determine the truthfulness of a tweet. So we need to come up with these features manually. Similarly, we can come up with features related to user reputation and more features related to user reputation and so on and so forth. And then eventually we come up with a table like this, right? So the number of likes, the number of retweets. So we are talking about computer programs, right? Computer programs can process numbers. So everything has to be converted to a number. So for instance, if you want to factor in the sentiment of a tweet, right? Whether it's positive or negative, that also has to be a number. It cannot be a word, right? So everything has to be converted to numbers, and then we generate this kind of a table of features. So these features vary, right? You cannot expect all the tweets to have a constant number of likes or a constant number of retweets, right? So these features vary. So these columns are really variables because they vary, and they vary randomly. We cannot predict easily the number of likes that a tweet is going to get. So they vary randomly. So each of these columns is modeled as or treated as a random variable, right? So column 1 is random variable x1, column 2 is random variable x2, so on and so forth. So we have all these x1, x2, x3 random variables. So we need to generate a model from this. So how do we generate the model? Like I mentioned, model typically comprises of a bunch of parameters. In some of the extensive deep learning algorithms, models, there are millions and billions of parameters, like the GPT-3, the recent deep learning model for natural language processing, has billions of parameters, right? So, but to start with, this is a simple example. So what we do is we get the X values for our data items. Like, for instance, say this is one tweet. We determine the x1, x2, x3 values for that tweet. So we determine the number of likes, the number of retweets, and all that stuff. And then we pass these to a summation function. So one thing to note is that these features are not all equally important, right? So you take the number of likes, number of retweets, number of replies. These are not equally important. They should be weighted. We need to generate relative importance to these features, right? So that is the whole point in machine learning algorithms. Machine learning algorithms basically determine the weights for each of these features, the relative importances of these features. So those weights are called W, right? W for weight. So there are as many weights as there are features, right? There is an initial weight, which is called the bias, because every system is associated with some amount of bias. Why? Because what is bias in the real world? It is assumptions. It stems from the assumptions, simplifying assumptions that we make, right? Like, for instance, we make a simplifying assumption that certain regions or certain ages are better at doing certain things, which is a highly simplified assumption. So that's a bias, right? So every system has some bias, particularly these kind of machine learning models where there are parameters, there is a bias because we assume certain things. In this case, we are assuming that these can be linearly combined. So that's what we are doing here, right? We are combining each of these feature values with the weights and generating a summed, weighted sum of the features. And W0 is the bias, initial bias, because of the assumptions that this model makes. And the assumption, like you see, is that these are linearly dependent, or the Y value is linearly dependent on these features, which is not obviously true. So we pass the weights and the features to a summation. We generate the summed features, sum of the weighted features. But this number is not going to be between 0 and 1, right? We want a number to be between 0 and 1 because we want to predict the probability of a tweet being true or false. So how do we convert this big, gigantic number, which is a sum of weighted features, to lie between 0 and 1? Can you please mute?
看不知道，对。
Was that a question or? Okay. Thanks. Please stay muted. That will help in the continuity. So how do we convert this to a number between 0 and 1? We pass it through what is called as a logistic function. So logistic function, when you plot it, it's in the shape of S. So all functions in the shape of S are called sigmoid functions, and logistic function is one such function. So we pass this weighted sum through this, and this number gets converted to a value between 0 and 1, right? So that 0 and 1, the value between 0 and 1 is the probability that the tweet is true or false. So that is the whole idea. Obviously, this is not going to be accurate, 100% accurate, right? So there is a loss. The loss is basically the difference between what you expect and what this model actually generates. So there is a loss. And this loss needs to be minimum for the model to be accurate. So we compute a loss, which is a function of weights. Remember, we have to determine the parameters, these weights. So the loss function, it's a mathematical function. It's a function of the weights. Typically, loss is based on the difference, right? What is the loss when we sell something that we bought earlier? It is the cost price minus the sales price, right? Same thing applies here. It is the difference between what is expected and what is actually generated. But it is too simple. That kind of a loss is too simple to learn from. So the loss is slightly more involved. But the essence of loss is basically this. It's still the difference. But to make the models learn better, the algorithm learn better, the loss function is slightly more complicated, right? So once we have the loss function expressed in terms of the weights, it is just a matter of solving the maxima minima problem, right? It's like a maxima minima problem where we need to minimize the loss with respect to the weights. So it's like partial derivatives. You take the partial derivatives with respect to weights and minimize the loss. So this is a crux of how traditional machine learning is used for fake news detection. Of course, the trend today is in the last decade, not today, but for the last decade, the trend has been to use deep learning. And deep learning typically uses several of these units that you are seeing on the slide. It uses several of these units in a very ingenious manner, and it can do wonders. So the advantage of deep learning is that the feature extraction, the feature engineering, the feature extraction is all automated. So we don't have to do this stuff. So like we did here, we don't have to determine these kind of features. All these features are implicitly determined by the deep learning algorithm. So that is the beauty of deep learning. So here's the interesting part, right? So these are the results of the Google Scholar search. So I just searched machine learning and fake. It resulted in 103,000 results. So, I mean, depending on the underlying Google search algorithm and the papers themselves, the results themselves, the numbers may or may not be very accurate, but the search results are quite indicative, right? So it is obvious that the problem has attracted tremendous interest from the research community. There is people have tried all sorts of techniques in deep learning and machine learning, traditional machine learning, to try to solve this problem of fake news. Several articles that I surveyed report outstanding successes. So in one of the papers, the authors claim that the experiments resulted in 100% training and testing accuracy on one data set, but on a different data set, the training and testing accuracy are 99.8 and 44.15%. So on one data set, 100% accuracy on training and test, and the other 99.8% and 44.15% training and test accuracies. So there are a whole lot of results like this. A fake news challenge, FNC1, was organized in 2017 to seek machine learning, natural language processing, and artificial intelligence solutions to combat fake news. So there are plans to organize a second version of this challenge as well. Let us look at the website a little bit. So if you look at the fake news challenge website, let us look at the FAQs. They are quite insightful. So they use, the challenge is basically described as stance detection. So stance detection is basically determining the truthfulness of one piece of information as it relates to the other piece of information, right? So when somebody tells us something, what do? We try to cross-check with some other piece of information, right? If we don't trust somebody, we try to check it with somebody else, right? So that is the idea behind stance detection. So they use stance detection. And then there's a whole lot of questions about stance detection. Why do you do that and all that? You can actually click, how did the fake news challenge originate? So there's a lot of interest. What I mean to convey is that there is a lot of interest in this problem. If you notice this slide, this kind of indicates the techniques or approaches that have been explored in the literature, the machine learning and deep learning approaches that have been explored in the literature to solve the problem of machine learning containment. This is just a sample, actually. But if you do search in Google Scholar, you'll probably end up in almost every possible technique being explored for misinformation containment. So the details are sketchy, but the claims are clear. Of course, there is some reason for doing that, because artificial neural networks serve as universal function approximators. What does it mean? It means that you can approximate any function, take some inputs and tell that this is going to be the output. This artificial neural network is able to come up with a function which maps the inputs to an output, to the outputs, right? We all know the meaning of function, mathematical definition of function. The function maps a set of inputs to a set of outputs. So that's what neural networks do. They can, given a set of inputs and given a set of outputs, you can literally come up with an approximate function which will convert the inputs to the output. So that is the beauty of artificial neural networks, which are the basis for deep learning. So it certainly makes sense that researchers have explored this intractable problem using machine learning and deep learning. So essentially, misinformation containment can be framed as a function of the features of information that outputs whether the information is true or false, or a degree of truthfulness. So if you go back, let me go back to that slide. So this whole box can be thought of as a function, mathematical function, right? What is this function doing? It is taking a bunch of x1, x2, x3 feature values and outputting a probability which is between 0 and 1. So this is a function. So this function, of course, here we used a very simple function, the logistic function. but you can go as complex as possible. This can be any set of numbers, not just the features, but pixel values, for instance. This can be amplitudes of an audio signal, anything. So you're given these inputs and you want these outputs. The deep learning framework can come up with a function which will map these inputs to the output. So that is the beauty of deep learning. So misinformation can be thought of as a function, basically. The problem of misinformation containment can be framed as a problem of determining the function between the inputs and the truthfulness. So that is the essence of all these models, particularly the deep learning side of things. But even for feature engineering, many approaches have been explored. And learning types also, many types of approaches have been explored. So, but the interesting question is, why is still the problem unsolved? We all know that this problem is hardly solved today, right? So, I mean, one can say that it is probably a reflection on the quality of research, not completely trying to solve the problem, but solving a portion of the problem is what is being attempted, maybe. So that is one way to look at it. But to understand the reasons why all the research hasn't been successful, there is a need to understand the nature of misinformation. Unlike spam, which can be detected based on the occurrence of certain word patterns and things like that, misinformation is highly complex. It is hugely a challenge, even for human beings, to detect misinformation, right? For instance, it can take years for truth to be established in a court of law. And there are cases which have been running for years, right, for want of truth, right? So it's a hugely complex problem. So it's not just a simple thing like spam detection. So let us look at some of the reasons. So truth is temporal, subjective, and relative. We all agree with this, right? So there were times when the truth about the earth was that it is flat, right? People believed that the earth was flat, and people who questioned that belief were put to a lot of trouble. And there are people who believe that the truth is that God does not exist, which is subjective, right? We don't know the real truth. It is entirely subjective. And there are objects that are small only when compared to other relatively large objects, right? So the truth is really relative in that respect. On the other hand, so that is a problem. The problem is that the truth is temporal, subjective, and relative. And on the other hand, machine learning models used in the current literature are fixed. Remember, in the model that we talked about, the parameters are determined using maxima, minima, calculus, derivative, partial derivatives, and they are fixed for the entire model. For all the training set, they are fixed. Once it is determined using training set, for the remaining data, it's all fixed for the life of the model, right? And therefore, these models cannot handle the dynamic variations in subjectivity or relativity of truth, right? The model is fixed, but the truth is changing. So the dynamic variations are not being handled by the models, machine learning models. So that is one problem. And determining truth can require a huge corpus of prior knowledge across multiple domains, right? Like we talked, the court cases run for years together. Why? Because there's a whole lot of information involved. Truth can be determined only after cross-checking against a huge corpus of established facts, evidence, and reasoning across multiple domains, right? This multiple domains is very important because misinformation in political domain, you take misinformation in political domain, it could involve health domain also, particularly with all the politics going on with the pandemic today, you can as well relate very well, right? That misinformation spans across multiple domains. But unfortunately, most of the machine learning models in current literature are incapable of such cross-checking across multiple domains. There are some solutions which propose cross-domain checking, but there are some limitations. The other topic that comes to mind when it comes to truth is the logic, right? First order logic. So first order logic is probably more, and probably even other formal methods. They have the implements to reason and inference from prior statements. Whereas machine learning models don't have those capabilities. So that may be one of the limiting issue. So I hope the contrast between the requirements and what the machine learning models provide is coming through these slides. So the next thing is, next point to remember is truth can evade feature engineering, right? You do a lot of feature engineering, extract all the features, and develop nice machine learning models. But truth can evade feature engineering. For instance, the same source of information with their features intact can produce conflicting statements. We all know that, right? We have seen that there are several cases where a user on Twitter posted conflicting tweets. Today he says something, after 3 days he says something totally different. But the features of this person haven't changed. The features that we engineered from Twitter for this user haven't changed. So merely extracting the features, whether manually engineered or automatically generated by the hidden layers, as in deep learning, are unlikely to flag the misinformation, right? So deep learning is basically a huge neural network or a reasonably large neural network with units like we saw before, right? So there are units like this, but a number of them. That's what makes it a deep learning framework, right? So merely extracting the features, even using deep learning, is not going to be sufficient. So the feature set used in a substantial part of the literature is limited to either temporal or contextual or content-based context, whereas the need is for a much more comprehensive and exhaustive information, right? Then misinformation is often seamlessly interwoven with truth in ingenious ways. See, this person we talked about, Andre Sepulveda, he was able to fool millions of people, right? They believed that what he was talking was the truth. Similarly, the YouTube video that we saw, right? It had millions of views. So why? Because the misinformation is very cleverly interwoven into the truth. So even the intent and purpose can sound very genuine for misinformation. In machine learning, some of the techniques that are used are latent space mapping, self-supervised learning. So these are approaches which give insights into the data, right? So these approaches have been used for misinformation containment also, but they can help only to some extent. They are not always accurate or exhaustive, right? I can go into the latent space mapping and self-supervised learning, but if I had to give a very quick example of self-supervised learning, it is used in Google searches. Let me give a very simple example, right? How does Google search, when I type fake in the search string, how does it know that it is same as misinformation? How does it associate fake with misinformation? That is done through what is called as self-supervised learning. It's again a neural network. Remember, deep learning framework is a universal function approximator. You can approximate any function. So the function that self-supervised learning approximates is to map words to their inherent representations, their latent or hidden representations. So those kind of techniques obviously come in very handy with misinformation containment, but they're very limited. Like I mentioned, they're not accurate or exhaustive. Then there are other limitations of the machine learning models. So typically, recurrent neural networks are used for language understanding, right? And recently, convolutional neural networks. So these are two very famous types of neural networks. So RNNs and CNNs, as they're popularly called, and other language models also. A model is basically a representation of something, right? So language model represents the language, English language. So this language model converts the words to numbers. So these kind of language models that are often used for natural language understanding cannot capture long-term dependencies in large texts. So even the latest transformer-based models like BERT, B-E-R-T, which is behind the Google search. BERT is an algorithm deep learning framework that was invented by Google. And that's what revolutionized the search, right? If you have seen in the last 5 years, the Google search has improved a lot. And one of the techniques behind that was BERT, B-E-R-T. So these models like BERT are only good for 512 tokens. That means 512 words in text. And there have been efforts to make it increase to 2048 tokens. So that's about it. But our text can contain thousands of words, right? So modeling that kind of data, that kind of text is a big challenge when it comes to understanding the language, right? So the current models mostly use this kind of language models, which are kind of limited. And then the other most important point to remember is that there is no silver bullet. Misinformation containment is not a single problem to have a single do-it-all solution. Misinformation is manifested in many modalities and forms. So the papers in the literature simply come up with a model and then propose a solution, but that's not enough. Each manifestation needs to be addressed in one or more ways. The current approaches address the problem by experimenting with a sample data set in a single domain typically. And this data set is usually identically distributed. That means it's like a probability distribution, right? When you generate the numbers, those numbers are all identically distributed. Then they use these numbers, generates a model, statistical model kind of thing. I mean, machine learning is all math anyway. So building models around numbers, right? So they build this model and run the model against new data, report the results from the same data set, and portray general success based on these results. So that's the reason probably why some of the accuracies are reported are up to 100%, which is very unusual in my opinion. So on the other hand, misinformation is far from being identically distributed, right? Misinformation is quite complex. You cannot think of the information being drawn from the same identically distributed data set. So I wanted to also highlight this op-ed in New York Times, where the authors claim that no, artificial intelligence won't solve fake news. And this was in 2018. And it is 2022, but nobody, the research in artificial intelligence continues to solve fake news. So the quotation is from this article is existing AI systems that have been built to comprehend new accounts are extremely limited, lacking a robust mechanism for drawing inferences or a way of connecting to a body of broader knowledge. Which is somewhat true, but let us not give up hope. There is still hope. So in summary, solutions must go beyond the traditional dataset collection, training, validation, and test cycle. So similar problems such as spam, viruses, cyber attacks, and other malicious implements are in reasonable control, but not misinformation, which is really a reflection on the complexity of the problem. State-of-the-art deep learning frameworks in general are computationally expensive and require humongous data, right? All deep learning models. Some of the deep learning models I mentioned require billions of parameters. Obviously, the billions of parameters require humongous data. And once trained, the essential parameters are fixed. Of course, transfer learning and some other new paradigms help in this respect, but newer patterns are still not modeled as much as they should be, particularly when the data is still evolving. Misinformation is evolving rapidly, right? In different forms. And static feature extraction for subsequent classification using parametric methods, it does not really model the evolving nature of misinformation. Misinformation containment needs to be continuous, instantaneous, and it should evolve with the changing patterns in the data. It should use less resources. For instance, somebody sends a message on WhatsApp, which is, it can cause panic, right? So even before that message goes through hoops, we should restrict it. So that means that it should use less resources. The the smartphone should be able to detect whether this post on WhatsApp is true or false. These models should be able to be deployed on the edge, like the edge computing. So those are some of the requirements. There are some promising developments we are currently working on, but it's a bit premature to give more insights. But I'll be able to shed more light in the next year's NFIC, hopefully, depending on the theme and other priorities. And you're welcome to collaborate with me on these or any other projects. And if you have any questions later on, my details are on the website shown here. And now I am open to any question and answers. Questions. Any questions? So I don't see any questions on the
chat. Yeah, I didn't see any question from the chat window. Yeah.
Yeah, there are no questions on YouTube either.
Okay. I'll put.
Vishnu,
Yeah. Thanks, Vishnu, share with this information. I think in this social media age, I think how to detect the misinformation. That's the key to protect the people and avoid from the lost information. Yeah, it's really help us. So I would like to present the certificate to you. Thanks for your time and with us. Yeah, thanks, Vishnu.
Yeah, thank you, Gary. Thanks for the opportunity.
Yeah.
Okay. Vishnu, is it okay? I ask one quick question?
Yeah, please.
Go ahead. Yeah.
Yeah. It's very interesting that you said that in the future, people try working on how to use machine learning to solve this fake news and misinformation containment. Do you have any classical problem that?
Rockwell, Can you speak loudly because we?
Yeah, I'm not able to hear.
Oh, sorry. Apologize. My microphone was put away. Okay, my question was, is there any classical problem that machine learning community try to use it as an example to determine there will be a solution, there will not be a solution using machine learning to detect the fake news? It is such a problem there that people try to solve as a benchmark. Because fundamentally, like you mentioned a couple of slides in your presentation, yeah, it's kind of very challenging to identify. Because like you said in Twitter, the person had one saying and today, maybe 3 days later, they may change the mind, right? So, but in the community, is there any a classical example that people try to solve to answer the question?
Yeah, that is where the research is happening. In fact, I'm also trying to work on that problem. There are some ideas, but they are still ideas. There's nothing concrete. So that is the reason why I'm not able to shed more light on those kind of solutions. But yeah, there is a plan to address the issue that you mentioned.
Mm-hmm. Okay, so no very good classical example today to be identified.
Yeah, there's no like a silver bullet kind of thing solution.
Okay.
Yeah.
Thank you.
Yeah, thanks.
If anyone have any other questions? Yeah. If no, and then the next topic is the YOLO V4 and its application. YOLO is the first the object detection model, and it's already widely used in our daily life, from the traffic control, production line, and there's a lot of application already. And there's also a lot of hardware accelerator is supporting the YOLO model. And YOLO version 4, its development and the lead it's developed by the Dr. Mark Liao and his team. Yeah, Dr. Mark Liao is received his Ph.D. degrees in electrical engineering from the Northwestern University in 1990s. And in July 1991, he joined the Institute of the Information Science Academia, SICA, in Taiwan. He has worked in the field of the multimedia information processing, computer vision, pattern recognition, multimedia application, and artificial intelligence for more than 30 years. He was appointed and honorary chair professor of the National Chiao Tung University from 2016 to 2019. He received a lot of awards from the Academia, SICA, TECO, and IEEE. He is also the editor of the many IEEE magazines. For example, Signal Processing Magazine, Image Processing Magazine, and etc. He also has been an IEEE fellow since 2013. Yeah, let's welcome the Dr. Liao to give us the talk.
Okay. Let me first of all share my slides. Can you hear me?
Yeah, I can hear you. Yeah, I can see you.
All right. Let me like we had did a test last Friday. Let me know whether this screen is correct, or I should reverse it.
You need to reverse. This is the presenter view.
All right. Now, is this correct now?
Yeah, it's correct. Perfect.
Okay. All right. All right. Thank you. Let me start from the first slide. All right. Okay. Today, the topic of my talk is the process of the birth of YOLO V4. And this is my great honor to deliver this talk. Later, I will show you some recent result. Okay, since open source, YOLO v4 has a great impact on science and scientific research in various fields. From September 28 to December 15, year 2020, YOLO v4 was the most accurate and speedy object detection algorithm in the world. It defeated the teams coming from Google, Microsoft, Amazon, Facebook, and Qualcomm. In year 2021, Louis Bochart surveyed and reported the 28 best AI work in year 2020. YOLO v4 was ranked #1 in that year. Okay, and my research team was awarded a 4-year funding of USD 280K per year, starting from January year 2018 to December year 2021. The Ministry of Science and Technology strongly urges all teams to implement, let industry raise issues, and let academia solve them. Since the Ministry of Science and Technology strongly endorsed cooperation with industry, we decided to collaborate with the listed integrated circuits company, Yilong Electronics. We hope to integrate software and hardware to develop smart city traffic flow solutions that are applicable not only to Taiwan, but beyond. Okay, so we set up some objectives of this small sponsored project. First, we would like to bring academic research and the development capabilities into industry. Second, we would like to commercialize artificial intelligence technology, let the products enter the international market. And the third one, which is the most important one, we would like the world see Taiwan. Okay, so the project team has several consensus. First, we select the real world issues given by the industry and try to solve them in a scientific way. Second, the team members should not only think about publishing papers, try to introduce science into the problem-solving process. And YOLO v4, as I mentioned, was the fastest and the most accurate object detector for 2.5 months during year 2020. And out of 180 teams listed on the leaderboard, it defeated the teams coming from Google, Facebook, Amazon, Microsoft, and Qualcomm. And here are the top 6 teams on the leaderboard. There are in total 180 teams. The competition was based on Microsoft Cocoa data set. As this slide shows, our CSPNet, which is which is the backbone of YOLO v4, ranked #1, #2, #4, and #6 in this competition. Efficient DAT ranked #3, detectors ranked #5, and those ranked between #7 and #10 are all Google teams. Okay, in this slide, it is shown how YOLO v4 can quickly perform object detection. This video was prepared by our co-author, Alexei Pochkovsky. He is now working for Apple. Okay, let me stop here. Now I would like to talk about the most sponsored project, Smart City Traffic Flow Solutions. The two parties involved in this project include the Institute of Information Science, Academia Sinica, and the listed integrated circuit company, Yilong Electronics. Okay, the goal of this project are roughly as follows. Yilong Electronics installs two different types of camcorders at 5 consecutive intersections on a main road in Taoyuan, Dayuan, which is close to the airport. One is a 360-degree fisheye camcorder, and this camcorder is responsible for computing the traffic flow within a depth of 80 meters at the intersection. The other type of camcorder is a gun-type camcorder. In each intersection, they allocated 4. It mainly calculates the traffic flow from 4 directions. Through the exchange of traffic parameters between intersections, traffic signals can be dynamically controlled. Okay, the first year of our project is to use fisheye camcorders to perform traffic flow analysis at intersections. In this kind of environment, the most important problem to be overcome is how to perform deep learning in the distorted visual space. Okay, the red circle in the left image of this slide shows a 360-degree fisheye camcorder. The image on the right is the intersection image taken by the fisheye camcorder. Okay, the computing tool provided by Yilong Electronics to the R&D team is NVIDIA Jetson TX2. Because the computing power of TX2 is only 5% of that of GTX 1080 Ti, it can only use limited computing power to maintain fast enough calculation speed and accuracy. And this is the biggest challenge we have to face. And what this video clip shows is the vehicle detection system developed by our team. In Yilong Electronics also deployed fisheye camcorders and gun-type camcorders in many places in Taiwan, including Taipei, Hsinchu, Taichung, Tainan, and Suao. In addition to deployment in Taiwan, Yilong Electronics has also deployed the information camcorders in Vietnam, Philippines, and Singapore. Starting in June 2019, our team began to develop traffic flow detection software for gun-type camcorders. The goal is to develop a lightweight deep learning-based neural network model that can effectively calculate traffic flow on the edge. Okay, and with YOLO V4 software embedded in the gun-type camcorder, one can use it to quickly and effectively detect traffic flow. The YOLO V4 we developed can detect various vehicles, 430 frames per second. During the night, YOLO V4 can still efficiently detect most of the vehicles. Okay. As mentioned earlier, fisheye camcorders and the gun-type camcorders can use YOLO V4 to detect traffic parameters at intersections. If the traffic parameters of the connected intersections are transferred to each other, it can be used as the basis for dynamic control of traffic signs. Therefore, one can easily build an intelligent road network system via assistance of YOLO V4 and related software. Okay, and this is the bird view of 5 consecutive intersections in Taoyuan, Dayuan. We expect to dynamically adjust the traffic signals by passing traffic parameters between road and the intersections. And this table lists the details of each year of our smart traffic flow solutions. Judging from the goals of each year, the first step of almost every item requires object detection. In the following, I will detail the process of how YOLO-V4 was developed. Okay, all right, and this is an example of using YOLO-V4 algorithm for detection of ventricular septal defects in ultrasound images. And this work has been published in International Journal of Interactive Multimedia and Artificial Intelligence. And here's an example of applying YOLO-V4 algorithm in malaria parasite detection in sick blood smell microscopic images. And this work is to perform fully automatic assessment of knee alignment from full leg X-rays. And it is also possible to perform melanoma lesion detection and segmentation based on YOLO-V4 darknet and active contour. And YOLO-V4 can also be applied to help computer-aided diagnosis of brain tumors. Okay, so our collaboration project with Yilong Electronics mainly focus on traffic flow solutions. Okay, using YOLO-V4 as object detector, the system we developed can perform blind zone object detection. This can remind the bus driver in due course to avoid traffic accident. Okay, the following I want to talk about is the inter-institution PM 2.5 research project of the Academia Sinica. The members of this project are mainly from Academia Sinica, and some members are from universities or medical centers. The number of vehicles and the pedestrians are directly correlated to the concentration of PM 2.5. In each window here, traffic flow can be detected in real time by YOLO-V4 algorithm. Using YOLO-V4, we can directly estimate traffic volume using online streaming videos. And YOLO-V4 can also be applied to count the number of people within the field of view. This factor also influences directly to the concentration of PM 2.5. In the following, I will report some YOLO-V4 related results. Use of oriented YOLO-V4 to perform detection and tracking in aerial images. The original design of YOLO-V4 can only have a bounding box that is not able to rotate when a vehicle is making a turn. In this work, my former student, Professor Su Zhiwen of Zhongyuan Christian University, designed a bounding box that can rotate when a vehicle makes a turn. Okay, here is an example of full range vehicle tracking. The object bounded by a white bounding box is car. Motorcycles are bounded by yellow bounding boxes. The object bounded by red bounding boxes located at the lower right and the lower left corner are pedestrians. Okay, we can use vehicle trajectories in all the areas swept by vehicles to perform traffic analysis. Okay, burying beetle behavior analysis research was conducted by colleagues from Biodiversity Research Center of Academia Sinica. Okay, with the assistance of YOLO-V4 detector, the analysis time significantly reduced from more than 3 months to 2 weeks. Okay, and YOLO-V4 can also be applied to many application domains other than traffic and medical treatment. For example, it can be applied to perform identification of underwater organisms and microorganisms. And this is about real-time fruit detection in the county based on YOLO-V4. And this work is about flower detection and the recognition using mobile phone. And this work was published in Automation in Construction, year 2021. It is about railroad track components inspection based on Euro before. Okay, and it can be also applied to real-time detection of breach cracks. Also in PC board detection, defect detection. Okay. And this work is about uneaten fish feed detection. It can effectively reduce feed waste and the water pollution. Okay. And this is about the flame and smoke detection for UAV based on Euro before. Okay. Next, I will detail the development process of Euro before and the scale Euro before. The three authors are from left to right, Dr. Wang Jianyao, Alex Sipochikovatsky, and myself. Okay, conventional object detection is very different from deep learning-based object detection. The former has to define handcrafted features and then identify corresponding object in an image. The latter, on the other hand, can be handled in an end-to-end manner. Okay. To implement a deep learning-based object detector, we need to train a deep network with a large number of training data. The training will end whenever the deep network is stabilized. During the object detection stage, an unknown image is input into the deep network for object detection. See left image. And the right image shows the recognized object in bounding box. In the right image, a person is recognized with the probability of 64%. The above mentioned deep network was developed by Joseph Redman in year 2015, and which is commonly known as YOLO. Okay, deep learning-based object detector is mainly divided into two categories. One is one-stage object detector, and the other is the two-stage object detector. The main difference between the two is their head. The head of one-stage object detector uses dense prediction, while the head of two-stage object detector uses sparse prediction. Generally speaking, the main body of deep learning-based object detector is divided into three parts, among which the backbone is responsible for feature extraction, the neck is responsible for feature organization, and head is responsible for making appropriate prediction. Okay, so next I will talk about how the backbone of Euro v4 is developed. Okay, in year 2018, we tried to develop first version of the backbone, and it was called the partial PRN, partial residual network. Okay, and PRN couldn't beat YOLO v3 and the M2 that much. We started to design a new network called cross-stage partial network in in the middle of year 2019. And this network is abbreviated CSPNet. The design concept of CSPNet is still based on gradient flow division. Okay, and this slide shows a complete architecture of one computational block in CSPNet. In order to develop a lightweight object detector that can be used at edge, we proposed this cross-stage partial net. The main concept is optimization of the transmission strategy of gradient flow for the backpropagation process of a CNN. We released the codes of CSPNet in November year 2019. The maintainer of DARknet, Alex Sipochikovatsky, found this outcome and asked Dr. Wang Jianyao to run the codes on different GPUs, including Maxwell, Pascal, and Volta. The CSPNet design can enrich combination of gradients, maximize gradient variability, and cut down the amount of computation. Okay, If we incorporate the design concept of CSPNet into the state-of-the-art object detection algorithms, for example, the combination of CSPNet and the ResNext 50 can reduce floating point operations by 22%. As for the combination of CSPNet and the DenseNet 201 elastic, the cut down of the floating point operations can be 19%. If one only considers the frame rate, bringing in the concept of CSPNet can significantly improve the AP50 by 6.3% in the SunderNet case, 4.1% in the CenterNet case, in the 12.1% in the PZ case. Okay, so let me roughly summarize what is new in YOLO v4. YOLO v4's architecture is CSP darknet. Okay, and it can enhance learning capability of CNN. And we have two nets. One is SPPNet. It can increase the receptive field and separate out the most significant context features. And the other net is PNet. And instead of feature parameter net used in YOLO v3, we use PNet. It is responsible for parameter aggregation at different detector levels. And as for head, we use the same head as YOLO v3. Okay, and this figure shows the comparison of YOLO v4 with state-of-the-art algorithm run on Maxwell GPU. Based on the Microsoft COCO dataset, the horizontal axis is the frame rate, and the vertical axis indicates average precision on the left and AP50 on the right. And this is a case for the Pascal case. And here shows the result run on Volta. Still, YOLO v4 beats all state-of-the-art algorithms in terms of speed and accuracy. So what can YOLO v4 series do? YOLO v4 has been applied to different application domains, including traffic flow calculation, social distance estimation, and group behavior analysis in sports. In what follows, I will show some demo videos that are grabbed from YouTube. Okay, this is a case for tiny YOLO v4. Okay, they both with the resolution 800 by 800, and the result shown in the left is the result grabbed by tiny YOLO v3, and the right hand side is YOLO v4, tiny YOLO v4. Apparently, the result shown on the right is much better than the result shown on the left. Okay, and here is a demo of scale YOLO v4. Okay, so next I will talk about what changes does YOLO v4 make. Okay, before our data has to send to cloud, so system could not send back in real time. But now with YOLO v4, system could do real time computing at the edge. Before, the equipment are very expensive, because the cloud system usually costs $1 million US dollars, and it's really bad because it's with high power consumption, larger than 300 watts. But now with YOLO v4, we can have embedded system to do the job. So the equipment is relatively very cheap. Okay, several $1,000s can do, right? So and also the power consumption is low. It's less than 30 watts. That means before rewrote the rules of the game with less than 30 watts power consumption, 430 frame per second throughputs, and we have precise real-time analysis. Okay. The last slide I will show you a video. It's an interview by Formosa TV Press. Okay. And this press conference was held July 2nd, year 2020.
Academia Sinica has teamed up with a Russian developer to build a super-fast, highly accurate object detection system. The system, called YOLO version 4, is already in use in Tun-Wen and Shenzhou, where it helps resolve traffic problems. It can also be used to detect whether people are practicing social distancing. Let's take a look. As soon as humans enter the frame, this object tracking system calculates the distance between them. The boxes are green when people keep at least 6 feet apart. This system can also detect whether the people are wearing masks.
Application can be anywhere, right? Anywhere, including biology and medical treatment in different areas, as long as there's a need of object detection. For example, there's an example about social distance. They use the detector as a first stage and detect the human beings walking within the field of view and try to calculate the distance.
The AI-based real-time object recognition system is called YOLO, which stands for You Only Look Once. The original version was created by Joseph Redman in 2016. The fourth version, the latest one yet, was developed by Alexei Borovsky and 2 researchers from the Academia Sinica, Wang Jianyao and Mark Liao. It uses artificial intelligence to detect objects, track and judge much faster and more accurately than before.
Usually we say real-time means it's 30 frames per second. Currently, YOLO V4 is able to achieve 430 frames per second. That means 10 times faster than human beings.
One of the biggest applications for the system is traffic image recognition and traffic flow analysis at intersections. The technology has been installed in Tun-Wen and Hsinchu.
So this road intersection can detect real-time information and pass this information to each other, so that we are able to dynamically control the traffic light without the intervention of human beings.
Researchers have moved to allay concerns over privacy and security concerns over the new technology.
Because it can complete all the calculations directly on the H end, so the data will not pass through people. You don't have to worry about the privacy of the people at the intersections, or worry that what you do in the car will be seen by others. The data is all handled by the machine on the local side and will not be uploaded to the cloud. It is relatively safe and privacy is protected.
Since the release of the open source code in April, tens of thousands of people worldwide have tested and applied the algorithm. For Taiwan, it's a milestone in computer engineering, as well as a big step toward developing smart cities. Formosa News, Stephanie Yang, Liao in Taipei.
Okay, I finished my talk, and it's a Q&A time. I am happy to take questions. Hello.
Yeah, thank you, Dr. Liao. It was very insightful, and of course, it's a great breakthrough. Really appreciate you taking time to talk to us today. I don't see any questions on the chat, either on YouTube or on Zoom, but I had a question myself. So YOLO 4 was a great breakthrough. So what else has been happening? Because we have YOLO 5 and YOLO 6 also, I believe, right?
Yeah.
So what else is happening in this area?
Well, actually, YOLO V5 was developed by one of the colleagues, one of the colleagues who also maintain .NET, right? And he's a Spanish, and he's also a friend of Alexei Podkovatsky. In basically, we developed the YOLO after our development of YOLO V4. About a month or 2 months later, he developed the YOLO V5, and it's taught PyTorch based. And YOLO V4 was .NET based on .NET 53, right, together with the CSPNet. But the developer of YOLO V5 didn't write a paper about the development process. As to YOLO V6, it was developed by Meituan, which is a company of Chinese company, Meituan, but they didn't publish a supporting article. Okay, so of course they did write a letter to 3 of us, including myself and Alex Podkovatsky and Dr. Wang, seeking for approval of YOLO V6, and we wrote them a letter indicating the formal version of the YOLO series should have underlying theory and some support experiment beating state-of-the-art algorithm in the past or object detection algorithm in the past. But they didn't publish any paper. So we told them YOLO V6 can be an unofficial one. All right, so 1 week later, we released YOLO V7, and that's the whole story.
Oh, okay. Thank you. Thanks for the insight.
Yeah, we released YOLO V7 in July 7th.
Oh, so
this year, year 2022, and Meituan, the Chinese company, wrote us the later and late June.
Oh, that's just a month back, I think.
No, just 1-2 weeks, because they have already released the YOLO V6. So we spent 3 more days to run based on what their environment their environments and write and run a set of experiments to tell them we are better than theirs. Yeah.
Oh, okay. So there is an interesting question on the YouTube chat. Prakash Ramchandran is asking, is YOLO V4 applicable to autonomous driving, self-driving cars? If yes, how, say, vehicle to vehicle or V2I can, how does it work for V2V or V2I? Can it be mounted, installed on like onboard boxes in vehicles to help autonomous driving, or its support is limited to ITS?
Well, actually, the implementation, I didn't involve in the implementation details. It was done by Dr. Wang, and I'm too old to know these details. But our algorithm is definitely, because we are working with the Yilong Electronics, so they have some demand on tiny YOLO V4 and tiny YOLO V7. So we try to cooperate with them and develop based on their need. But these parts we didn't release.
Oh, okay. So thank you, Dr. Liao. I am pleased to present a small token of our appreciation for you. It's a certificate recognition.
Yeah.
We will this out to you. Thanks a lot for taking time today, and it was really very insightful, very motivating for the
Thank you. All right, thanks a lot. Thank you.
Thanks. So we'll now move on to the next talk in our schedule, which is on 3D digital pathology-inspired artificial intelligence for precision diagnosis. So the synopsis is digital medical images for training AI models have made major impact on precision diagnosis, among which digital pathology transforming glass slide glass-slide stains to whole slide images. So these are WSIs, whole slide images. Facilitates systematic analysis of tissue morphology and biomarker distribution. Integrating thick tissue staining, 3D image scanning, software and deep learning algorithms, we have retrieved hundreds more high-resolution digital images with spatial features from each clinical biopsy to develop novel AI models for precision diagnosis of morphology variation, tumor recognition, and biomarker expression. So the speaker's breakthrough technologies will support matching right patients to right treatment, contributing to precision medicine. We have two speakers presenting this talk. The initial part will be done by Dr. Tun-Wen Pai. Dr. Pai earned his Ph.D. in electrical and computer engineering from Duke University, Durham. MS in electrical and computer engineering from Johns Hopkins University, Baltimore in USA. And presently, Dr. Pai is the chairman of Computer Science and Information Engineering, National Taipei University of Technology, NTUT, Taipei, Taiwan. Dr. Pai has published a number of papers which are available on request. And the rest of the talk will be done by Dr. Yen-Yin Lin. Dr. Lin earned his PhD, MS degrees in electrical engineering and BS degree in nuclear science from National Tsinghua University, Hsinchu, Taiwan. Presently, Dr. Lin is the CEO of Gelox Biotech Incorporated in Taiwan itself. His previous work experience includes as the Chief Executive Officer, MOST, Industrial Valve Creation Program to develop AI and image inspection system. This is for Precision Anatomy Research, Brain Research Center at National Tsinghua University in Taiwan. Can everyone please mute if you don't have a question? Dr. Lin has been a visiting fellow, research fellow at Stanford University in California, R&D consultant at Microtech Instruments in Oregon, visiting research assistant at Brookhaven National Laboratory in New York. Dr. Lin's publications include 47 papers in prestigious journals, more than 80 plus conference papers, out of which 3 of them are invited speeches in first year with 10,000 plus participants in the conference, 1 worldwide webinar hosted by the Optical Society of America, and 16 issued USA Taiwan patents. Dr. Lin received the following honors. He received the 2022 Boehringer Ingelheim Grassroots Award. In 2021, he received the 20th Business Startup Award. Again in 2021, Gold Award, Entrepreneur Warrior Competition. He also received the Future Technology Award, MOST in Taiwan in 2021, and several others. In 2007, Dr. Lin received the Outstanding PhD Dissertation Award from the Optical Engineering Society of the Republic of China and Taiwan. He originated several novel laser systems such as novel electro-optic laser Q-switch. It's a US patent. Quasi-phase matching, PDT, PDD laser sources, it's a Taiwanese patent. Cascaded quasi-phase matching QPN laser service. This again is a Taiwanese patent. So let us welcome our presenters, and over to you, Dr. Pai and Dr. Lin. Please take it over.
Thank you. Thank you, Professor Pendyala, for your introduction. And Dr. Lin, could you please share your slides? Thanks. Okay. This is Tun-Wen Pai from Taipei Tech, National Taipei University of Technology. And before Dr. Lin's presentation in 3D pathology topics, let me quickly introduce what we have been doing in medical application. Yeah, this is me, Tun-Wen. Okay, next slide, please. Currently, there are many projects conducted in Taipei Tech by a few professors. And here, I just quickly, briefly introduce. There are two projects we are ongoing project we are doing using AI computational technology algorithm in medicine application. Okay, could you 4 slides, please? The next slide. Dr. Lin, can you change the slide to the next one? So there are two projects I'm going to introduce. The first one is cross-staining histopathology image segmentation for breast cancer area detection, and using UNet-like architecture. Actually, the problem is described as the following. There is no fluorescent annotated image database to be trained for a prediction model for fluorescent image. However, a couple of H&E pathological image database can be used for prediction model training. So the idea you try to use H&E hematoxylin erosion image as our training model and predict the nucleus element in fluorescent image. So here we use mobile net and UNet architecture, and we do some pre-processing techniques to combine this recognition techniques. So we use color decomposition first, and then use our own developed adaptive color segmentation algorithm to transfer the H&E image into a specific channel, and then use this kind of object to train a prediction model. After that, we perform on fluorescent image, and also we perform on H&E image recognition as well. So the result, you can see a prototype. We have pop up some preliminary result. It's for the based on H&E trained image system. We can recognize the nucleus in fluorescent image. The recognition accuracy can be increased from 50% to 80%. And however, because this cross-staining recognition, the original H&E image recognition accuracy rate will be decreased for some pair of is decreased from 97 down to 90%. So we are going to give more design and then try to improve this recognition rate. So the next one, the second project we are doing is use some DNA methylation biomarker to provide early precision diagnosis. For currently, we focus on urothelial, the bladder cancer, and the other one is colorectal cancers. So how we do this? So if you look at this whole system architecture, from the upper left part, it's we so-called it's primary biomarker detection. It is discovered the candidate biomarker from the whole genome gene chips for DNA methylation from the DNA methylation chips. For human genome, there are about 850,000 DNA methylation probes and loci. So how we identify the efficient biomarker from those 850,000 probes, and then as our specific biomarker, we perform differentiation analysis. And for example, for the bladder cancer, we perform on 440 genome profile, and we can extract about 500 biomarker candidate. And then it's not enough. So how we restrict this biomarker to a more reasonable number of biomarker for the medical device. We had to lower down the number. So we pop up the other idea, use comorbidity analysis. So we use National Taiwan Health Database and try to understand for different target disease, they have different comorbidity and different trajectory pattern. So we use a machine learning algorithm to find out all these associated disease. And from this associated comorbidity, we can identify their gene, disease gene marker. So from there, we combine these two primary biomarker and secondary biomarker. We can narrow down the efficient biomarker for realize the medical device. So, for example, for the colorectal cancer, after these two primary biomarker and secondary biomarker intersection, we have only 48 gene left. Okay, so and for the bladder cancer, we have only 101 biomarker left for further clinical validation. And it's still a lot for this result for these two modules. And so we apply the attention-based mechanism and try to ranking all these selected biomarker. For example, we use a functional clustering process to clustering all these candidate biomarker into different function groups. And then from each function group, we rank in all these biomarker and then see their strengths for this specific target disease. And then choose one representative biomarker from each grouper, from each functional groups. And then after that, we only have 3 biomarker left for clinical validation. For example, in colorectal cancer, we have 3 gene. One is the ADHFE1 and the SDC, and the other one is the PP2 R5. And use this 3 gene biomarker, we use detect on the stool. Okay, important message is we just use non-invasive specimen. For the colorectal cancer, we use stool fecal to evaluate the methylation status. And for the bladder cancer, we use the urine. Okay, these are all non-invasive approach. So for the bladder, for the colorectal cancer, based on these 3 selected biomarker and their methylation tested result, we can reach 84.6% sensitivity and 92.3% specificity. So it's quite a very a great performance. And for the bladder cancer, now it's still under clinical validation. And so far, we have after the AI-based attention-based learning model, we choose 21 gene, and then we perform all these 21 gene. And if we choose any 3 of the biomarker from this 21 gene, the accuracy can be reached 91%, and for the specificity of 100% and sensitivity of 83. However, this is the sample validation. So we perform on liquid biopsy for the urine specimen. And the specificity for one of the best biomarker can reach specificity for 93%. And the sensitivity could be reached 87%. So it give us a very great result so far. So we now we are going to collect more sample from the cooperative hospitals. So after that, we can make a decision which 3 will be the best combination for the early precision diagnosis for this urothelial and the colorectal cancers. So I think from this architecture, we can see the lower left, there are another 2 modules will be involved in our project. One is the spectral photometrics evaluation from the urine. We are going to test is there any blood in the urine, and the other one is the cytopathology analysis. So from the urine as well, we can look at from the microscope and see their morphology of if there's any cancer cell appear in the urine. So we are going to combine all different type of the feature, and then try to train a comprehensive prediction model. And after that, we can provide the patient and doctor a good reference for their current status. So why we do this? One, the important message is all non-invasive detection. So if you use the traditional way to detect your cancer, the tumor size should be at least 1 millimeter, and then you can see it from the a CAT scan, a radiology scan. And however, when you see the tumor so big, it should be at least a stage 1 or stage 2. So it's a little bit too late for the treatment. So if we can find the early diagnosis of the cancer, maybe in your body, the DNA methylation, the microenvironment already tell you the truth. You have this kind of a bad situation. You have to go further detection, not use when you have the obvious symptom, and you have to take like the cytoscope, protocol scope. It's all invasive detection, and it's very painful. So this is our project goal: try to find an effective and efficient biomarker to detect the early cancer. Okay, so I think I just give a quick introduction of the two projects. What we are going to do now. If you have any interest, please just contact me through my email. Okay, so let's turn to today's topic: 3D pathology-inspired AI for the precision diagnosis. Thank you, Dr. Lim. So you can continue, please. Thanks.
Dr. Pai, do you want to answer questions now, or you'll take them towards the end?
I think we can answer later after this complete the presentation.
Okay, sounds good. Thanks.
Yeah. Okay. Hello, everyone. Thanks for the invitation to provide a talk about our company's developments. First of all, how to build up new data from 3D pathology is our goal, and the more data means that the AI assist diagnosis is important for the future's developments. Okay, the first part is that what is our company's goal is that we would like to integrate the diagnosis data platform based on the 3D pathology. Why we say that currently the next generation's genomics testing and proteomics genetics testing are separated. All of them do the precise data, but without tissue structure information. Therefore, our company want to develop one technology. We can do the 3D tissue data firstly, and after that, and use the same tissue for the precision diagnosis testing. Therefore, our goal was setting by the two parts. The first part is that we would like to transfer the actual slide to the digital slides, because the most of the pathology diagnosis still under the actual slides reviewing. And the second part is that currently pathology slide is 2D, so we would like to upgrade the conventional 2D image to the 3D images for the high precision diagnosis. So for this kind of platform can benefit three different targeting audience. The first part is that physicians can get the normal diagnostics informations and can use to match innovative therapy to cure patients. The second part is that the pharmaceutical company can use our platform to find the new biomarkers. The new biomarker is very important for the new drug development to find a new drug for the cancer diagnosis, for cancer treatment. The third one is the patients. The patient need a more affordable and available health monitor solution to expand their lifespan. So the unmet medical diagnosis need is that the conventional pathology workflow only can record 0.4 to 1% biopsy tissue as to product the diagnosis report. That means that most of the biopsy tissue need to be reserved for others exam, for example, next generation sequencing or proteomics exam. Yeah, so that means that you can only use 100 to 200 tumor cells for each diagnosis report. It is quite ridiculous because each tumor at least own 10,000 tumors in a single tumor. So you just only take a very few tumor cells to judge the morphology and distribution of the tumor is not reasonable. So we develop a new technology. First of all, we don't need the slicing anymore, and we can use the 3D images to record all the tissue structure. After that, we can analyze the tissue images by the computer. Okay, this is our company's history, and thanks for the presider already introduced our results. So I just summarize a few information. The first of all is that in this year, our 3D PD-L1's distribution paper already be accepted. And according to our finding, combine 3D pathology and AI, we find that at least 40% of the patients need be carefully to evaluate their PD-L1 distributions during the real clinical data. And the second paper, 3D post-day paper already be accepted. We also prove that combined with the 3D tissue imaging and the AI can change the pathology report status. And what we are doing to do the 3D pathology, conventionally, the tissues is not transparent. So the right-hand side of the left-hand side of this slide, which shows the 200 microns breast cancer tissue is untransparent. We invent a reagent can make it become transparent. So we can use this transparent tissue, record their structure under the optical microscope. That means that the 200 micron in thickness means that at least 40 to 50 layers cell can be observed at the same time. Conventional 4 microns tissue just cannot observe a complete cell. Yeah, and all of this procedure already be satisfy the ISO and the FDA's requirement. And after that, we already do this project to combine with the conventional IHC, HE, and the genomics test, NGS test, the proteomics test, and can long-term observe the disease progress by the liquid biopsy. Combined with the AI, and we can use this platform to help patients to monitor their disease progress. And this concept also be granted by the Boehringer Ingelheim's pharmaceutical company. Yeah. So the next part is that we would like to show how we use 3D tissue imaging technology to build up a clinical standard of the 3D pathologies. The first part is that why we want to go to the digital pathologies. In the past, the pathologists use the real slide under the microscope to observe the slides. The problem is that it will be really difficult to re-examine the same samples at the same times. So the difference between two pathologies is up to 25% chance can provide different pathology report and the diagnosis results. So currently, people want to scan their real slide into the digital. In the digital, the benefit is that first of all, the two pathologies easier to negotiate and to discuss under the digital system. The second part is that we can use the computer to help the pathologist to pre-screen the spectacular tissues positions. So it will be very important to enhance and boost the overall process by using the computer. And the second part is that why we want to use 3D pathologies. According to the method we developed for the prostate cancer, our methods can finish the 3D structure images within 1 day. And by using this kind of technology, we can find the invasive glands around the stroma cells. So that will be easier to use the computer science and the AI to segment the interconnect tubular network. Of course, the single gland is also easier to be judged. For example, this single gland will represent a different stage during cancer's diagnosis. At the depths at the 18 micron to the 23 microns, because the sizes cannot be decided. So this solid tissue circle represent Gleason cell 3 or 4 stage. That means that the patient need to go to surgery to remove the prostate. But in the depths 28 to the 43, it will be clear to understand that this gland is empty. So that means that the patient cannot don't need to do the surgeries. So that means that use the traditional 2D slide will be difficulty to understand the real stage of the cancer patient. After doing the morphology's judgment, we starting to doing the comparison result in the lung cancer. Yeah, our experimental method is the upsize. The first we use the FFPE block and the section by the three slides. The first slide and the second slide is the conventional HE and the PD-L1 IHC slides. And the third slide, we use the 3D images to record the structure and the PD-L1 distribution at the same time. After that, we compare all of these 3 slides results. The lower side is the example to show the IHC staining and the PD-L1 staining for the superficial layer of the 3D imaging is identical. So we also compare all of the real slides difference. Okay, after we do this kind of 3D slide, we also need to verify the result is about after 3D pathology, can we reduce HE or IHC validation? It will be very important because in the clinical process, not only use the 3D pathology, but also we need to use regulatory validated method to export the report. The currently clinical validated method is the HE and IHC. So we need to make our tissue can be reused to do the HE and IHC. After do the validation, we know that this tissue can do the HE and IHC, and the remind tissue can be reused to do the PCR validations. According to us, our experiments, we also find that the PCR result cannot will not change by using our process. So all of these finishes. So we prove that our 3D tissue images can be used the first step for the pathologist exam. And after that, the IHC, and the genomics, proteomics, and the NGS exam can follow in the 3D tissue images. Okay, you get a lot of information, so you need to do the meaningful testing before doing the next exam. So the 3D tissues structure with the antibodies information is quite important. So our algorithm doing the 3D data analyze is divided by two steps. The first step is that we use the conventional machine learning, conventional neural networks to predict the tumor regions. The tumor regions accuracy is around 90%. After that, in this region, we use the object detection methods to detect all the cancer cells nucleus. After detect the cancer cell nucleus and use AI classifier to distinguish the PD-L1 antibody positive or negative. All of these three parameters collect together, and we can easily calculate the TPS score larger than 50% and 1 to 49% and less than 1% 3 regions. Why we want to do this kind of exam? Because all of the new innovative treatments criterion is that you need TPS score larger than 50% and can satisfy the insurance reimbursements. So we're doing this kind of exam. And we find that the 3D TPS can show a new benefit. First of all, this 3D imaging, we can find that in the tissue at the 25 micron, you can see any antibodies expressions. But in the 130 micron, you can see a lot of PD-L1's distribution. That means that the distribution can be changed with the tissue dips. So after we finish the 33 case, we find that a lot of the diagnosis results cross different categories. That means that the maximus TPS result and the distribution of the TPS result is different with the currently pathology diagnosis report. And what's the difference to do the 3D TPS? We would like to show this result by two cases. Yeah, these two cases in the clinical is that all of them IHC TPS report is 0%, but in the late stage of their disease, they all of them use the immunotherapy by treating by the NEMOs. But the clinical response is different. One of the clinical response is stable disease. Another is a partial response. That means that the case 3 and the case 33 and the case 35 is exactly identical, but their clinical response is different. So we want to find the reasons. After our AI and the 3D images screening, we find that the case 3 and the case 33 and the case 35 result shows the different 3D distribution. Case 33 is always keep their expression lower than the normally lower than the 1%, and the averages TPS result is only 1.5%. But the case 35 shows much higher, is 8 times higher percentage than the case 34. So that means that the case 35's chance is larger than the case 34. So that means that if case 35 can doing the 3D imaging, 3D pathologies imaging plus AI's diagnosis, have a chance to use the NEMO at the early stage. So the clinical treatment result can be better. So I would like to do a briefly conclusion about these sections. In these sections, we show that from the 5 of the 33 biopsy specimens, we find that the PD-L1 tumor proportional score varies by larger than the 10% by using the computer diagnosis. In the 14 case, we find that the 14 case means that the percentage is 42.4. The TPS score will be divided in the different region. So that means that the currently patient screening process may be not sufficient to doing a good reference for the treatment decision. Okay, so in these parts, we want to futurely we can use kind of this method to do the more clinical response and the 3D's pathologies distributions connection and connections results. Okay, and the next one is that how do we can get this solution to the hospital? The first part is that we think that the digital pathology currently most of the hospital use the central large computer as a major direction. So we would like to use the edge solutions to instead of the edge central computer server. Yeah, because this method is much easier for the pathologist to make a new technologies. And we remove the GPU's budget and collaborate with the Intel by using the OpenVINO and the OpenFL structure to make the pathology can easily use a new technology for their digital pathology diagnosis. After that, our software can provide a lot of AI-assisted annotation and the 2D to 3D imaging viewer, and of course, then provide analyze reports. All of that, we also consider the speed. By using the Intel OpenVINO structure, we can boost up the calculation speed 37 times. And all of the systems include tumor recognition, invasion detection, in the immune system evaluation and the TPS evaluation. So all of this AI model already equipped in this system. And this kind of system is not can be directly accepted by the hospital. Hospital needs a different hospital cross reference. So we will also use kind of this edge device to make a different hospital can through our edge device to communicate each other and build up the new AI model. And this direction is quite simple. By using visual learning's OpenFL structure, two hospitals can communicate each other. And the data from the two hospitals can be training a single model. So this model is quite valuable and be recognized by two different hospitals. Okay, so this kind edge device and the 3D pathology plus AI system can be used for the clinical education research and trial developments. And currently, we already demonstrate this system in the Chang'an Memory Hospital, Mackay Hospital, and the National Taiwan Universities hospitals. And all of these hospitals can training their AI model with others image data. Yeah. So thanks for your attention. And it's welcome to meet with our company at the Intel Innovation 2022. This event also held in the San Jose, and in the end of the September. Yeah, you can reach me by the email. Thank you.
Thank you, Dr. Lin. I think your talk generated quite a bit of interest in the audience. There are quite a few questions. So the first question is in vitro biomarkers simulations computational only, or are they real?
Okay. Currently, all the biomarkers information is real staining by using the antibody. But part of the our experiment result shows that some of the antibody can directly use the AI model to predict the staining regions.
Okay. And the next question from Pat is for the non-invasive detection method of colorectal cancer, how soon do you think this technology will be available in the general market?
Yeah. So how to wear that?
Go to market.
Oh, how to go to market? Yeah. So for the bladder cancer and colorectal cancer, actually we have the project supported by Taipei Medical University and Taipei Tech University. And recently we just demonstrate their result. And for the bladder cancer, we need more clinical validation. And after that, we are going to actually the patent already undergoing. Okay, for the United States for the colorectal cancer, and bladder cancer is preparing. So yeah, so we have to file the patent first, and then we just cooperate with the hospital, and we use this LDTS is laboratory development test. So it's not necessarily go through the FDA, but it can be supported by a lab to demonstrate the result and provide the result to the hospital as a reference. Okay, so it's easier to promote this product, medical device.
Okay, thanks. Switching back to the YouTube chat window, the other question we have here is how to introduce these gene biomarkers fed into human body? Is it via tablets or some drinks, or how does it enter into the body? Should I repeat the question?
Can you show the problem again?
How do we introduce the gene biomarkers into the human body? So how does it go into the inside the body, human body?
No, we don't need any this kind of process. We just take the human stool sample or the urine samples, and then extract the DNA fragment, and then perform the qPCR. It's chromatic methylation specific PCR. We only perform PCR experiment outside human body. So you don't need invasive into the human body at all. So that's a very, very key point. So that's the reason we need a more clinical validation, because our data come from the TCGA, the NIH database. It's all tissue sample, tissue biopsies. However, we use this whole genome gene chips differential analysis, and then we obtain all these candidate biomarker, and then we use this candidate biomarker and test on the stool and the urine only. So we don't need to do any invasive process. Just validate this our suggested biomarkers. Is that the answer to the question?
Yeah, I think so. And the next question we have is, does healthcare system in Taiwan, or is healthcare system in Taiwan able to use your digital pathology techniques currently? And how does it improve outcomes of the treatment? Do you have any survey reports or results to share? If you want to add anything to this.
Jane, can you answer the question?
Okay. Yeah, currently I would like to introduce the system we use in Taiwan. Firstly is that all the regulation validates pathology method is traditional HE and IHC. So our 3D pathology can predict and pre-check the tissue distribution before doing the HE and IHC. So for the hospital, actually they are doing an extra test before the real HE and IHC examinations. Yeah, so they can use the 3D pathology to do the pre-screening. And the second part is that the most challenging part is that how to realize the digital pathologist value, because conventionally for the pathologist, they can judgment by using the microscope. However, the problem is that the conventional method have some sampling error. The sampling error is not caused by the pathologist. So if they adapt our system, they can use the 3D images to analyze the whole tissue. So that will be easier to create more chance to treat the patients. So that's why they are happy to use our digital pathology system to doing the new diagnosis. Yeah, they can doing the extra benefit. They can provide extra benefit to the patient, and they also can create more treatments business for the hospital. Yeah.
Thank you, Dr. Lin. It was really very interesting and very exciting talk. I gathered a lot of interest as well. So it's our honor to present you with a small token of appreciation. If this was in person, we could have presented a plaque to you, but this being a virtual presentation, I'm very pleased to present this recognition certificate to you. We will email this out to you. And this is for Dr. Pai. And for Dr. Lin, this is the certificate. So thanks again for taking time today to give us a talk in the New Frontiers in Computing conference. Thanks again.
Thank you.
Yeah.
Thank you very much. Thank you.
Thanks. So we now move on to the next presentation, which is the trends in securing AI data pipeline. So we all know machine learning and deep learning are part of artificial intelligence. Machine learning models apply labels to data or collect samples dynamically and curate them. So data needs to be clean and relevant for building or optimizing models and delivering the analysis and inferences that lead to improve the accuracy of the results with greater optimization and making them more human-like intelligent, yet applying MLOps. So we apply MLOps, automation, and efficient delivery for multiple domains and use cases. In the data pipeline from various sources, data can be compromised, and there's a need to secure them. So the speaker here is going to lead us through the causes and biases that can be controlled through use of best practices and share with us the trends in securing data pipeline and artificial intelligence. The speaker is Prakash Ramchandran. He is leading Emerging Open Tech Foundation, EOTF as it is abbreviated, as the co-founder and secretary since 2020. The objectives of EOTF are helping the Indian subcontinent in its digital and operational transformation. He is the co-chair of INGR's Edge Service Working Group, focused on next generation networking beyond 5G. He has been doing this since the year 2019 from Silicon Valley. And as part of NFIC from IEEE Computer Society Silicon Valley chapter and a constant promoter of IEEE and NATEA partnership over several years, he has held leadership positions. He was the vice chair of our chapter. He has over 4 decades, 40 plus years of ICT industry experience in the US, European Union, India, and Asia Pacific, and has led several startups and managed technically and innovated as ISP, ASP, CSP companies for decades. His insight into data analytics and AI is equally formidable and has several presentations in open source forums globally. He holds a master's degree in EE, electrical engineering, from the reputed IIT Bombay, Indian Institute of Technology Bombay, which is a premier institute in India. So over to you, Prakash. Please take it away.
Can you hear me?
Yes.
Is this clear? Okay. So I can share the slides. Okay, let me go ahead and go to the desktop, share my application. So here it is. I can hopefully, are you able to see my slides? Do you want me to do in the mode which is, let me see, where is the mode to, is it visible to you, everything proper?
Yeah, it's all okay, but you can share, you can put it in the sharing mode, right?
Okay, yeah, I did put in the share mode, but is it, you mean to say, one sec, you mean to say, where is this? I thought where is the slide transition, slide layout, background, transition. So I want to move in the slide presentation mode I want, right?
Yeah.
So where is the presentation mode? I'm a bit struggling here. Maybe somebody can help me. Can you see my screen first?
Yeah, we are able to see the screen.
Action, where is the action to?
Yeah, there should be a button there. I'm not.
Okay, let me see whether I can. Conversation action. Where is it?
So type, top right corner, there should be something.
One sec, forward, back, print. Where is the run mode?
No, there's a drop down, right, to the top right.
Okay, you have to say in the
No, not there. In your browser itself, top right. If you go all the way to the right, there is a drop down. No, drop down. Okay, let me annotate.
Yeah. You can try the control. It's okay with enter.
Okay, I'll just continue if I find it. But yes, so I'm looking here at the securing a data pipeline. So to put it, so thank you, Vishnu and all the NATEA team for allowing me to speak. First, we have to look at the data, deluge data which has been expanding like mad. So data growth figures from IDC indicate that we are in the something like 67 exabyte per month, which if I which is from mobile, and overall it is around 85 exabyte per month. That was in 2021, and if I go by year basis, it is reaching something like 1020 or 1040 exabyte, which is equivalent to zettabyte. So we are already in the zettabyte era per annum basis. And at the global level, we can see the percentage. Global is around 22% cumulative CAGR rates growth, and therefore by 2027 we are going to get the approximate. Today we are finding in 1 year we are getting zettabyte, and this zettabyte will be done in 3 months, because we are getting around 368 exabyte per month. In 3 months it will cross 1000, which will become exabyte. So we are going to get 4-fold increase in the matter of just another 4-5 years, and so it's all humongous data. This is obvious from Ericsson report, Cisco reports, as well as from the IDC report. So I'm just quoting a couple of reports to say that data is the new oil. So that's what people say, and that is the reality. So when you see data so humongous, you have to extract information out of it through pipelines. Like in oil, what we do, we send from the source to the destination. Same way here, the data is coming like rushing, and so we need to get the data into proper pipeline to be able to process it. And so if that is what, because data has more interpretation from analytics as well as from business intelligence, as well as from the various presentations you saw from Vishnu to the people here before the medical, we can say everybody needs data, and data, not fake data but real data. And the challenge here is when you get the data, how do you source it? So there are diverse sources, and that include the source from example a cloud provider database, or it could be from a Google like Analytics, and so all of these needs to be acquired and stored somewhere after processing. So you always have an acquisition process of data, relevant data, and then you process them. Either you do extract and then convert them. So you can see that there are necessity for certain objectives to be met, like the size, the latency, the bandwidth, and the volumes in kilo to zettabytes or exabytes. So how do we get the raw data, whether we get it in comma separated value or fixed width frame or other file system, and then if you are applying an API to the source, then it could be collected as a RESTful or API JSON based or something like that. Now the data itself is a variety of data, because media types can be different. It can be text data, image data, 3D, video, voice, Ethernet. So it can be in various formats, as well as we can collect in batches or we can collect as a stream of data. So, and ultimately these end up being collected and stored into either some kind of a SQL database like MySQL, could be spreadsheet or Hadoop file system, depending on the bigness of data, whether it's big or medium, large, etc. And volume, velocity, all that is important. So first thing in the data pipeline is to clean up the data. So if you have some orphan records, or if you have duplicates or missing records, or some inconsistent format, or mislabeled or unlabeled data, then you need to require them to be cleaned up for, and that is the process where you validate data for the extract transform load, which is the most common. ETL and ELT are the more common patterns that are used for BI and ML pipelines or data warehouse, and this is then followed by what you call some kind of a analytics applied on them, and they apply and retrieve and store them in the database. So this is simple data collection from source, transfer, do some processing, and load them into the storage, and that's kind of a data collection and cleaning and storing process. Now, the analytics can be run offline, can be run online. So let me move into the data transformation portion of it. So you can transform the data, extracted data. Example, a simple thing like time zone. If you have data from Taiwan time and from Pacific time, then you need to convert to GMT or something like that, so that there is a time correction there and applicable, so that we can evaluate the data correctly. Same way you can have for the time series data, you can do 15 minutes. Usually telcos use that, so that you can collect in a aggregation form every 15 seconds, the counts, etc. So that is kind of some of the conversions that you would like. Similarly, when you say modeling, then what you want to do, you may want to represent one or more tables of the collected data when you store and transform them based on the business or whatever processing logic you want. Example of other personal security, privacy, etc. You may want the email ID.
Prakash, I think we lost your voice.
Yeah,
Talking.
Prakash, we lost your voice.
Did you lose me?
Okay, now it is audible.
Okay,
Yeah,
sorry.
your voice has a little bit broken up. Is it because you are too close to the microphone?
Okay, okay. Can you hear me better now? Is that perfect? You can guide me. Should I come closer?
No, probably slightly far away.
Okay. So let me continue on there where I left. I was talking about the transformation and modeling, data collection, and then some of the cleanups or conversions. And then in the data modeling, I was trying to say that some business logic may be applied. Now, to do all this, as long as it is a simple one or two pipelines, it's okay. But when you end up with hundreds and thousands of pipeline, you need to do a workflow orchestration, task basis, because one task can be run in parallel, some tasks can be run in sequence, and it can be parallel sequence and all that. And based on the complexity of data pipeline, one needs to manage the efficient workflow. So there are tools available in the industry. Like example of them is like Apache Airflow, or it could be Argo, or some of this AWS Glue, etc., which are available in the cloud framework of either with Kubernetes or without Kubernetes. And essentially what happens is when you connect tasks, you form the nodes and you connect the nodes, then there is an edge and the node, and then there is a graph kind of thing. And since it is directed from source to destination, or depending on the dependencies, we call it as DAG. So that means directed cyclic graph. You don't do cyclic, but you make sure that it is like a tree structure, and you follow either the asynchronous or synchronous execution to work with those tools, and thus one is able to improve the performance, etc. Now, this I was talking about only the data, simple data transfers like your BI and traditional things. But when it comes to modeling, in terms of machine learning models, especially Vishnu spoke about the one of those like GAN and some of those BERTs, etc. So BERT is nothing but bidirectional encoding representation. So what happens is when you have a natural language processing, you have a sequence to sequence conversion. So if I'm speaking, suppose in English, and you want to translate it into Taiwanese, then obviously you have to go word by word and try to make meaning out of it and then translate it. And so this is where the BERT comes into picture. The usual RNN and CNNs are unidirectional. So you cannot really apply within the attention of the same line. Like example, Vishnu mentioned that currently limitation is 2048 words or something like that for a search in the Google. But that apart, whenever you can convert line by line, so hopefully you should still be able to do it. But if you have a line and next line, then you need to make sure that you are able to next sentence modeling also you are able to address. Not only that, if I say a line and then I miss something, then that is called masking. So you can give in a given line, like I'm saying today is, and then I skip. So we have to say Saturday. So, but how will it know that it is Saturday? So that is the discovery process. That is called embedding process. So you have a mask language model and a next sentence model. So BERT NLP model uses both the masking and the next sentence model and attention to self, that is the text which is there, current line, next line, and figure out what is the connection and then be able to put out the conversion. So if I have a sentiment analysis or this question answering or language translation example I give, you can use the incomplete sentence and you can predict the sentence. And usually decoders are used for the RNN CNN, but here the self-attention is more important. And so, and not only that, it can go bidirectional. So you can move in the sequence forward, backward, and then determine the context. And once the context is established, you can definitely predict in a better way. And that's what GPT-4, 5, and etc., whatever they are, which Vishnu mentioned, they are all going to try to improve the second generation BERT types of implementation. So BERT is one of the transformers, and transformers are the only thing why I am taking transformers is there are different models. Transformers is the best model which we can apply the pipeline very easily, and that's why I took this. And the next one I am talking about is GAN. GAN is a very popular one where what you do is like Vishnu was talking about faking and all. So actually here a generator tries to fake the sample data, but actually the sample real data example is known to the discriminator model. So discriminator tries to make sure that no fake is allowed to be used in the model, but ultimately when you keep on bombarding, generated model becomes so good that it can on its own be able to produce, and then discriminator model can be dropped out, then you can use the generator model to produce the sample. So it is domain specific, like text to image, image to image, music generator. One of the ones you can generate music using that by samples, and so all these image object recognition, computer vision, all of these use GAN models. So GAN is a obviously it is a generative adversarial network which is based on the game theory, and the game is between the discriminator and the generator, and you are able to produce sample data. Now this is good for domains where the data generation is harder, and like medical implementation, medical agro, and there are some domains which are very good for it, and one can use this as a model. So given the models, I just gave you two models. What is the impact how does it impact the security, and how does data disruption cause losses? So disruption of operation in ML pipeline causes significant damage to brand and reputation, impacts on the product safety, loss of theft of IP, and substantial fines are imposed by the government. So to protect these, one can do some of the things which are available in the industry, like obfuscation is very normal to do. If I have to give a rate, I put it on the web, I can just open what is required. I can include example, I can use a bluefish algorithm or something and hash it out. So the rate will not be visible in the communication. So protecting the by obfuscation is one of the methods. Then you can use biases and fairness through code. There are some like TensorFlow examples are there where you got 5 or 6 scripts which can be used for those. So every framework and every model has some or the other way to reduce the biases because of the classification or clustering, whatever you do. So that is one to avoid the what you call the impingement of biases or like we do in the faking, right? And so we want to avoid that. Similarly, managing access levels as needed because we need to make sure that we do two-phase authentication or API level protection, etc. And there is also some called as CVE or what it means is vulnerability is there, and that CVE is the measure you do the protection by having CVE scores. So there is a database available with the NIST and all where critical security breaches can be detected and fanned out to all the producers of the software and the ML, and that can be used by most of the people. And there is a critical one. Critical is 10. 0 is non-critical. There is nothing there. So based on the criticality, one can ensure that you can pipelines can be blocked, etc., to avoid any of those catastrophe losses and all that. So this is what we have, the certain modeling recommendation, and you can also for privacy protection. I have already said that you can do some of those what you call the data conversion and etc. So at the end of the this one, what I want to project is that we can close this with the ML modeling pipeline, which is generally you get a data ingestion, you do the validation, you do the pre-processing, you do the model training. There are tools available, example Kubeflow for the Kubernetes-based deployment, which is very common these days. Airflow is one of those open source, and then Beam. So these are all open source tools which can be used for pipeline orchestration, DAG creation, and also for the batch as well as for the streaming data. And based on the framework like TensorFlow, etc., obviously you have starting from ingestion, data ingestion to validation to processing to modeling. All this can be orchestrated in automated version, but analysis and validation requires a little bit manual, and then so is model deployment requires some modeling, some kind of a feedback loop to be able to. So total automation in MLOps is still a part of a process, but not everything can be modeled as yet because the consequences of what happens based on the learning is important. So at this stage, I think I should close my talk and just say these are the best practices and one can go through them, and we have only a few minutes left. I would like to close with these slides are available to you. You can go through. Versioning is one of the things which I missed in the beginning, and that is first thing is you must know what framework and what model you are using before you can apply all things to data pipeline. So that cannot be done by engineers, and that has to come from data scientists usually. Data engineering portion one can handle through data pipeline, but data science folks have to tell what is right, what is wrong, because it is scientific in nature and it is statistical. And it is not like programming where you program in a deterministic way. It is very undeterministic, and in fact, unsupervised learning is all undeterministic. So unless and until you do optimization or Pareto's multi-optimization, etc., and are able to reach the convexity or whatever, if it is convex or not convex, to reach the best possible optimization, then only you should be able to use it. So then only you can use it efficiently and effectively without wasting the energy and all that. So with that, I'll end and I'll invite our Gary to propose a vote of thanks or whatever. Vishnu or Gary, whoever it is. I'm done.
Yeah, Yeah, thanks, Prakash. Yeah, thanks your talk. I think this is a very important. AI is all related to the data and how to secure the data using the right data, and this data pipeline will be the important function. Yeah. And thanks for everyone. I think we almost we are a little bit behind the schedule, but thanks everyone. Thanks for all the speakers and the volunteers, our community members, also the audience. Thanks for your time. And what I would like to present the certificate to Prakash. Thanks to Prakash taking the time with us, share us a lot of
Thank you.
information.
Thank
you. In here, I learned a lot of things from today's talk, from this AI in the medical industry, then this YOLO version 4, this new application. They bring a lot of application, future application as well, and also Prakash, you're talking about all this AI pipeline and how we use the AI to detect the misinformation. Yeah, this is a lot of new industry. This is a new application. I can see we have a better future, and there's a lot of the AI application we can use in the future. So NFIC is a new event, and next year we will continue the NFIC 2023. I would like to give it to Prakash, to the Vishnu, to talking about next year. Yeah.
Yeah, thank you, Gary, and we really thank the NATEA staff and the Science and Engineering Taiwanese Association. We have great pleasure to be collaborating with you for 20 years. I'm thankful to John. He's not there probably here, but John Pugh was one of the founding members of this. And we are very grateful to work with you. And as part of our 50% of our one we do on NIDA and one we do on this next frontiers, new frontiers in computing. And it has been named. Sometimes they call it next, sometimes they call it new, but nevertheless it is emerging frontier, and that is important. And from this year, what I can say is that we have picked up data science and fantastic presentations previously by Vishnu also, and IEEE is very much part of this, and we are very happy that we can deal with Stanford as well as San Jose University and Santa Clara University. These three universities we have been rotating mostly, and we have to think of what university later, but the topics we do want to look at some of the 5G, beyond 5G, satellite communication, computational requirement for what you call edge in the air, edge in the space, and so Leo, Neo, Geo, those kinds of things, and computational requirement to reduce the latencies on ultra latency, low latency, etc. So we do have quite a bit of, and AI/ML is part of the 6G. Going into release 19, and I believe, and 18 and 19. And so we do see quite a bit of ambitious things available to us. Even quantum computing is another where we can take some peek. Depends on, there could be also like security, TSP. So there are many topics which we see emerging, and over a period of time we'll be able to assess that, and we are not in a hurry to immediately jump to anything. We want to have things settle, and hopefully the new committee and new team will come in, and we want to make sure that Vishnu is part of it. He has been a great contributor. I like his style of doing things, and so we have a good things to look forward to. I think with that I will thank all of you for putting all your hard work, and we are happy to see Gary come out emerge as a new leader, and hopefully we'll be able to guide the next year when we do one more of this. And with that, I will close on my. Vishnu, you want to say something?
Thank you, Prakash. Thank you, Gary. It was really a great session today. We had really outstanding presentations. So thanks to all our speakers today, and thanks to the organizers who worked with us in putting up this great show. So as you can see on the screen, we have been hosting NFIC since 1999, except for 1 year because of COVID-19. All other years, we had really trendy topics like Prakash mentioned. And this year we went virtual. Last year was also virtual. And this year, as you can see, we had registrations from several countries, 39 cities in several countries. So we will certainly keep this in mind for next year as well. Thank you all, and have a great weekend, great evening, or great morning, whichever place you are in. See you next year. Bye.
Thank you.
Thank you.
Bye.
Thank you.
Thanks, everyone.
Bye.
Bye. Bye.
Bye bye.
Bye.